You're drifting through space nearly 1,400 light-years from Earth. And ahead of you hangs a world that glows red-hot in the darkness, reaching temperatures no planet was ever meant to experience. This is WASP-12b, a gas giant planet nearly twice the size of Jupiter, orbiting so close to its star that the heat has turned its atmosphere into a furnace. The planet appears strange from this distance, distorted somehow, its shape wrong in a way you cannot quite identify yet, stretched toward the nearby star that dominates the sky. You are witnessing a world in its final million years, a planet being slowly consumed by its own sun, and the slow destruction of this world unfolds in the darkness around you. The star itself sits close, terrifyingly close by any reasonable standard for planetary orbits, separated from the planet by only 3.4 million kilometers. To understand how close this is, consider that Mercury orbits our Sun at about 58 million kilometers, and Mercury already experiences intense solar radiation and heat that would vaporize most substances. WASP-12b orbits at less than 6% of Mercury's distance, hugging its star in a tight embrace that generates temperatures exceeding 2,500 degrees Celsius on the side facing the star. The planet completes one full orbit around its star in just over one Earth day, racing around its sun faster than our planet rotates on its axis. You are listening to the Drowsy Astronaut, and tonight we explore doomed worlds, planets in their final days, places where the normal rules of planetary existence have broken down. We will move slowly through this journey, taking time to understand what you see here, to feel the reality of a planet being eaten alive by its star, and to witness the end of a world. But before we drift a little deeper, feel free to share where you're listening from in the comments below. It still amazes me to see how many different corners of the world these journeys reach. The planet WASP-12b waits ahead, glowing in the darkness, and we return to observe it more closely, to understand what makes this world doomed and what its fate will be. From your position in space, the planet dominates your view, larger in apparent size than Jupiter would appear from the same distance, puffed up by the intense heat into a bloated sphere of gas. The atmosphere glows faintly, heated to the point where it radiates visible light, the entire world acting like a vast, dim lantern hanging in the void. Clouds of gas extend around the planet in a hazy envelope, material from the upper atmosphere that has been heated and lifted away from the surface, some of it escaping the planet's gravity entirely. The color tends toward deep red and orange on the day side, cooler browns and blacks visible where the night side begins. The temperature difference between day and night measuring over 1,000 degrees, despite the planet's permanent tidal lock to its star. The planet's size seems impossible given its proximity to the star. The heat should have stripped away this much atmosphere long ago, and yet the world persists for now. The bloated nature of the planet comes from thermal expansion, the intense heat from the star warming the atmospheric gas and causing it to expand outward, puffing the planet up like a balloon filled with hot air. This expansion reduces the planet's density to less than a third of Jupiter's density, despite having similar mass, making WASP-12b one of the least dense planets known to exist. The low density makes the planet vulnerable, its weak gravity barely able to hold on to the expanded atmosphere, material constantly escaping from the upper levels where the star's gravity competes with the planet's own pull. Scientists discovered this world in 2008 using the transit method, watching as the planet crossed in front of its star and blocked a tiny fraction of the starlight. The discovery came from the Wide-Angle Search for Planets project, which gives the planet its catalogue name WASP-12b, a designation that lacks poetry but identifies this world precisely in the records. Ground-based telescopes detected the transits, the regular dips in the star's brightness, occurring every 1.1 days, like clockwork. And follow-up observations confirmed the presence of a massive planet in an extremely tight orbit. Since that discovery, telescopes including Hubble and Spitzer have studied this planet extensively, revealing details about its atmosphere, temperature, and the ongoing process of its destruction. The star that WASP-12b orbits appears as a yellow dwarf, similar in many ways to our Sun, with a surface temperature around 6,300 degrees Kelvin. The star contains about 1.4 times the Sun's mass and measures about 1.6 times larger in radius, making it slightly more massive and luminous than our home star. Age estimates place the star at about 2 billion years old, less than half the Sun's age, a relatively young star that will burn for billions more years into the future. The star itself shows no unusual features, no extreme activity or odd properties, just a normal yellow star living its normal stellar life, indifferent to the planet being destroyed in its gravitational grip. The planet's doom stems from the combination of proximity and physics, the nearness to the star creating conditions that no planet can survive indefinitely on cosmic timescales. Tidal forces, the same forces that cause Earth's oceans to rise and fall with the moon's gravity, act on this planet with tremendous strength. The star's gravity pulls harder on the side of the planet facing it than on the far side, creating a difference in gravitational pull across the planet's diameter that distorts its shape. Heat from the star expands the atmosphere, reducing density and making the planet even more vulnerable to tidal forces and atmospheric escape. The planet orbits so close that material from its upper atmosphere can escape the planet's gravity and fall toward the star, creating a slow but steady transfer of mass from planet to star. The planet loses approximately 6 million tons of material every second. Gas from its upper atmosphere stripped away by the combination of thermal heating and tidal forces. 6 million tons per second sounds enormous, and it is, by human standards, enough mass escaping every day to equal several times the mass of Mount Everest. Yet the planet itself contains roughly the same mass as Jupiter, about 318 times Earth's mass, giving it total mass measured in trillions of tons. At the current loss rate, the planet could theoretically survive for billions of years before losing all its mass. Except the planet does not have billions of years, because the orbital decay will destroy it much sooner than atmospheric loss would. The planet's atmosphere extends far beyond what you might expect, reaching outward in a huge envelope of hot gas that surrounds the planet for thousands of kilometers in every direction. Observations reveal the presence of metals in this extended atmosphere. Magnesium and calcium ions detected through spectroscopy as they absorb starlight during transits. These metals should have condensed and rained down into the planet's interior at these temperatures under normal circumstances. Yet the extreme heat keeps them vaporized and mixed throughout the upper atmosphere. The presence of these metals indicates how thoroughly the heat has disrupted the normal atmospheric structure, preventing the usual separation of materials by weight and temperature that occurs in cooler gas giants. Looking at WASP-12b from your vantage point, you can almost sense the instability, the way this world hangs on the edge of dissolution, held together by gravity that barely overcomes the forces trying to tear it apart. The planet exists in a state of dynamic tension, material constantly escaping, while new material wells up from below to replace it, the atmosphere churning and boiling under the relentless radiation from the nearby star. The night side of the planet receives almost no direct starlight, facing permanently away from the star due to tidal locking. And yet, even the night side maintains temperatures of 1100 degrees Celsius or more, heat transported from the day side by atmospheric circulation. The planet's orbit itself carries information about its fate. The precise period of 1.09 days measured to high accuracy through years of transit observations. This period represents the time it takes the planet to complete one circuit around its star, traveling at speeds of hundreds of kilometers per second in its tight orbit, held in place by the star's gravity pulling inward, while the planet's velocity carries it forward in a perpetual balance. Orbital mechanics dictates that this balance will not last forever. Tidal interactions between planet and star gradually changing the orbital energy and causing the orbit to decay, bringing the planet slowly but inexorably closer to its destruction. The doom is not immediate by human standards, but it is certain, written into the physics of the situation as surely as gravity pulls objects toward the ground. The planet's composition remains mostly hydrogen and helium, the same materials that make up Jupiter and Saturn. Light gases that formed the building blocks of this world when it coalesced from the protoplanetary disk billions of years ago. Heavier elements exist mixed into the atmosphere and possibly concentrated in a core deep within the planet, remnants of the rocky materials that may have served as the seed around which the gas giant formed. The exact structure of the planet's interior remains uncertain, the extreme conditions making it difficult to determine whether a solid core exists or whether the planet consists of gas and liquid all the way to the center, compressed by the weight of the overlying atmosphere. Watching this planet from space, you feel a sense of witnessing something rare and significant. A world in the process of being destroyed on timescales short enough that astronomers can measure the changes. The planet will outlive every human civilization that might observe it, persisting for thousands of generations into the future before its final destruction arrives. Yet, in cosmic terms, 3 million years represents a brief moment, a flicker of time in a universe billions of years old, making this planet's doom imminent by astronomical standards. The quiet tragedy of WASP-12b unfolds in silence here in the void. No sound in the vacuum, just the patient operation of gravity and heat slowly dismantling a world. The discovery of this planet, and others like it, has transformed our understanding of planetary systems and planetary fates, revealing that not all planets enjoy the stability of Earth or Jupiter. Some worlds are born into circumstances that doom them from the start, migrating too close to their stars through gravitational interactions or disk migrations that seal their fate. WASP-12b serves as an example and a warning, a demonstration of what happens when planets venture too close to their suns, when tidal forces and heat overwhelm the forces holding a world together. Scientists study this planet intensely, using it as a laboratory to understand processes that happen nowhere else, learning about atmospheric escape, tidal interactions, and the limits of planetary survival. As you continue observing WASP-12b from your position in space, the planet's distorted shape becomes more apparent. The way its form deviates from the perfect sphere you expect for a gas giant. The planet has been stretched, pulled into an elongated form by the same tidal forces that are slowly destroying it, and this shape tells a story of stress and deformation, of a world being torn apart. The egg-like distortion points toward the star like an accusation, the planet reaching toward the very object that causes its demise. And understanding this shape requires exploring the tidal forces at work, the physics of how gravity can reshape entire worlds when the conditions become extreme enough. The shape of WASP-12b reveals itself more clearly as you observe from different angles, and what at first appeared as a spherical planet shows itself to be distinctly egg-shaped, elongated along the axis pointing toward the star. The planet is not a perfect sphere like Jupiter or Saturn. Instead, it bulges outward on the side facing the star and extends less dramatically on the far side, creating an oval or ellipsoidal form that makes the planet about 20% wider along the line connecting it to its star than perpendicular to that line. This distortion is not subtle or theoretical. It is real and measurable, detectable through careful analysis of how the planet blocks starlight during transits and how its gravitational field affects the star. The egg shape represents physical deformation, the planet's structure warped by forces strong enough to overcome the natural tendency of large bodies to settle into spheres. Tidal forces create this distortion, the same fundamental physics that causes Earth's oceans to rise and fall as the moon orbits our planet. But here the forces are far stronger and the effects far more dramatic. Tidal forces arise whenever the gravitational pull on one side of an object differs from the pull on the other side, creating a difference in force across the object's diameter. For WASP-12b, the star's gravity pulls harder on the near side of the planet than on the far side, simply because the near side sits closer to the star. About 200,000 kilometers closer when measured across the planet's diameter. This difference in distance might seem small compared to the 3.4 million kilometer gap between planet and star, but gravity follows an inverse square law, growing stronger as distance decreases. And that relatively small difference in distance creates a measurable difference in gravitational pull. The tidal force stretches the planet along the line connecting its center to the star's center, pulling the near side outward toward the star, while the far side experiences less pull and lags behind. Imagine holding a ball of soft clay and pulling on opposite sides the clay elongating into an oval shape under the stress, and you have the basic picture of what happens to WASP-12b. The planet's material, gas, and possibly liquid in its interior responds to these tidal forces by flowing and redistributing, the near side bulging outward toward the star, while the overall structure deforms. The planet maintains some spherical character because its own gravity tries to pull it back into a sphere, creating a balance between the tidal forces trying to elongate it and gravity trying to round it out. Earth experiences similar tidal forces from the Moon, though far weaker than what WASP-12b endures, and these forces create the ocean tides that rise and fall along coastlines twice per day. Solid Earth also deforms slightly under the Moon's tidal pull, the ground rising and falling by centimeters as the Moon passes overhead, though most people never notice this because the deformation happens gradually and affects everything equally. The Moon itself experiences tidal forces from Earth, forces that long ago slowed its rotation until it became tidally locked, always showing the same face toward Earth. WASP-12b has likewise become tidally locked to its star, rotating once per orbit so that one hemisphere perpetually faces the star, while the other faces away into darkness. The amount of distortion, that 20% increase in width along the tidal axis, tells us how close WASP-12b sits to the limit of tidal survival called the Roche limit. The Roche limit represents the distance at which tidal forces become strong enough to tear an object apart, overcoming the object's own gravity and destroying its structural integrity. Every star has a Roche limit for every type of object orbiting it, the exact distance depending on the densities of both the star and the orbiting body, and on the strength of the body's own gravitational self-attraction. For a planet like WASP-12b, with very low density, puffed up by heat, the Roche limit sits farther from the star than it would for a denser planet, because the planet's weak gravity makes it easier for tidal forces to tear material away. WASP-12b orbits just outside its Roche limit, close enough that tidal forces can distort its shape dramatically, but not quite close enough to tear it apart immediately. The planet exists in a precarious state, its bloated, low-density structure making it especially vulnerable to tidal disruption. A denser planet of the same mass could orbit closer without experiencing such extreme distortion, its stronger surface gravity resisting the tidal pull. But WASP-12b's heat-expanded atmosphere and low overall density leave it weak against the tidal assault. The material at the tips of the egg-shaped bulges, the points where the planet reaches farthest toward and away from the star, experiences the weakest gravitational binding to the planet. And material from these regions can escape most easily. The distortion is not static. The planet's shape changes slightly as tidal forces continue working on it. And thermal expansion varies the size of the atmosphere over time as heat flows and atmospheric circulation redistributes energy. The planet breathes in a sense, expanding and contracting slightly, the shape fluctuating within a range determined by the balance of forces. Computer models of the planet's structure attempt to predict the exact shape, calculating how the gaseous layers respond to both gravity and tidal forces, how the rotation and the heat affect the distribution of material. These models generally agree with observations, confirming that the planet has been stretched into an egg form by tidal forces that will eventually destroy it. The elongation affects how we observe the planet from Earth, the egg shape changing how much starlight the planet blocks during transits, depending on its orientation. When the planet crosses in front of the star, with its long axis aligned with our line of sight, it blocks slightly more light than when oriented differently, creating subtle variations in the transit depth that careful measurements can detect. These variations provide additional confirmation of the planet's distorted shape, independent evidence beyond theoretical models that the planet really does look like an egg in space. The brightness of the planet itself varies slightly as well. The tips of the egg reflect different amounts of starlight, depending on their orientation, and on how much atmosphere exists at those elongated points. Understanding the egg shape requires appreciating how weak the planet's self-gravity has become due to its low density, and how strong the tidal forces are at this close distance. The planet's escape velocity, the speed needed to leave the planet permanently, measures only about 60 kilometers per second at the surface, much lower than Jupiter's 60 kilometers per second, despite similar mass, because the expanded size means the surface sits farther from the center, where the mass concentrates. At the tips of the egg-shaped bulges, where the planet reaches farthest from its center, and where tidal forces add to the outward forces, the effective gravity becomes even weaker, and material there barely remains bound to the planet at all. Imagine standing on a platform at the substellar point, the location on the planet closest to the star, if such a platform could somehow exist in the gaseous atmosphere. The star would fill a huge portion of the sky overhead, appearing about 60 times larger in diameter than the Sun appears from Earth, an enormous, blazing disk of light dominating your view. The gravity you would feel pulling you toward the planet's center would be partially counteracted by the tidal force pulling you toward the star, and by the centrifugal force from the planet's rapid rotation, making your effective weight perhaps only a fraction of what it would be at a normal point on the planet. Material at this location can escape the planet relatively easily, lifted away by thermal expansion and tidal forces, beginning its slow drift toward the star. The egg shape also tells us something about the history of this planet, that it must have migrated inward to this close orbit rather than forming here. Planets cannot form this close to their stars. The heat and tidal forces would prevent the accumulation of material in the first place, disrupting any planetesimal disk before a planet could grow. WASP-12b must have formed farther from its star, several astronomical units away, where conditions allowed gas giant formation, and then migrated inward through interactions with the protoplanetary disk, or through gravitational encounters with other planets. The migration brought it too close, into the region where tidal forces are strong enough to distort its shape, and where the star's heat prevents it from settling into a stable spherical form. The 20% elongation represents a significant deformation, the planet's shape deviating noticeably from spherical, and this amount of distortion indicates how close the planet sits to the edge of tidal breakup. If the planet were to migrate even closer, or if it lost enough mass to become even less dense and even more vulnerable, the elongation would increase until eventually the tidal forces at the tips of the egg exceeded the planet's gravitational binding entirely. At that point, material would stream away from those points continuously. Not just the slow atmospheric escape we see now, but a faster disintegration process where the planet sheds material in great plumes, beginning the rapid destruction phase that will eventually consume the entire world. For now, the planet holds together, its gravity just barely strong enough to maintain structural integrity despite the distortion. The egg shape representing a compromise between the forces trying to round it out and the forces trying to tear it apart. The balance cannot last forever. Orbital decay will bring the planet closer to the star over millions of years, and as the distance decreases, the tidal forces will strengthen, following that inverse cube relationship, growing rapidly more powerful as the gap closes. Eventually, the planet will cross fully into the Roche limit region, and when that happens, the egg shape will become even more extreme, elongating further until the structure fails and the planet begins to come apart. Viewing the egg-shaped planet from your vantage point in space, the distortion appears both beautiful and tragic, a world deformed by forces beyond its control, stretched toward the star that dooms it. The shape serves as a visible reminder that this planet is not in equilibrium, not stable, not going to survive indefinitely. The tidal forces that created this egg will continue working on the planet, gradually pulling it toward destruction. And the shape we see today represents just one moment in a slow transformation from stable planet to scattered debris. The egg points toward the star like an arrow indicating the direction of the planet's fate, reaching toward the object that will ultimately consume it. A geometric expression of doom, written in the planet's very form. The physics behind the egg shape applies to many other bodies in the universe. Moons orbiting close to their planets often show similar tidal distortion, their shapes stretched by the same forces that affect WASP-12b. Jupiter's moon Io, the most volcanically active body in the solar system, experiences extreme tidal forces that squeeze and flex its interior, generating the heat that drives its volcanism. Saturn's moon Enceladus likely experiences tidal heating as well, helping to maintain a subsurface ocean, despite the moon's small size and the cold of the outer solar system. But WASP-12b's distortion exceeds any moon in our solar system. The tidal forces here are stronger because the masses involved are larger and the distance is smaller, creating deformation visible across hundreds of thousands of kilometers. The egg shape of WASP-12b exists because of the star, the yellow dwarf that orbits just 3.4 million kilometers away. And understanding this doomed planet requires understanding the star that is slowly consuming it. The star appears normal, unremarkable in most respects, yet its proximity to the planet makes it the agent of the planet's destruction, the gravitational source creating the tidal forces, the radiation source heating the atmosphere to the point of expansion and escape. The star acts as both the planet's parent, the gravitational anchor around which the planet orbits, and the planet's executioner, the force that will ultimately tear the world apart. And exploring this star reveals how something so ordinary can create such extraordinary destruction. The star at the center of this system, WASP-12, appears as a yellow-white disk if you observe it from a safe distance. It's light, warm and steady, similar in many respects to our own Sun. The star contains about 1.4 times the Sun's mass, making it somewhat more massive than our home star, and this extra mass gives it a slightly larger radius and higher surface temperature. The surface temperature measures around 6,300 degrees Kelvin compared to the Sun's 5,800 degrees, hot enough to shift the star's color slightly toward white while maintaining the yellow hue characteristic of stars in this temperature range. Astronomers classify the star as spectral type F, close to the G type of our Sun, a star burning hydrogen in its core through nuclear fusion, just as the Sun does. The star's age, estimated at about 2 billion years, places it in the first half of its expected lifetime, of perhaps 5 to 6 billion years total, before it exhausts the hydrogen in its core and begins evolving toward the red giant phase. 2 billion years represents a young star by astronomical standards, formed about 2.5 billion years after the Sun formed, part of a newer generation of stars in the galaxy. The star likely formed from a molecular cloud enriched with heavier elements from previous generations of stars, giving it a metallicity similar to or slightly higher than solar metallicity, meaning it contains elements heavier than hydrogen and helium in proportions comparable to what our Sun contains. This metallicity played a role in allowing planets to form around the star, heavier elements providing the raw material for rock, metal, and ice that make up planetary cores. From the planet's perspective, if anything could see from within the planet's atmosphere, the star would appear enormous, filling roughly 60 times the angular diameter that the Sun fills when viewed from Earth. The Sun subtends about half a degree in Earth's sky, small enough to cover with your thumb at arm's length, while WASP-12 would fill about 30 degrees of sky as seen from WASP-12b, large enough that you could not cover it with both hands held together at arm's length. The star's disk would stretch across a significant portion of the visible sky, a wall of blazing light and heat dominating one entire hemisphere, the sheer size creating an oppressive presence that would make the star feel less like a distant sun and more like an overwhelming nearby object. The star emits radiation across the electromagnetic spectrum, from gamma rays through visible light to radio waves, and the intensity of this radiation at the planet's distance creates the extreme temperatures that have puffed the planet up and heated its atmosphere to the point of glowing. The total energy the planet receives from the star exceeds the energy Earth receives from the Sun by a factor of thousands, the closer distance more than compensating for the modest increase in the star's luminosity. This intense radiation heats the planet's day side to 2,500 degrees Celsius, hot enough to melt most metals and to vaporize many compounds that exist as solids or liquids at Earth's surface. The star's light carries not just heat, but also ultraviolet radiation that can ionize atoms in the planet's upper atmosphere, stripping electrons from hydrogen, helium, and heavier elements. The star's gravity, about 1.4 times the Sun's gravity at its surface due to the increased mass, extends outward to dominate the space around the star for vast distances. This gravity holds the planet in its orbit, pulling the planet toward the star, while the planet's orbital velocity keeps it moving forward in a perpetual balance between falling and moving. The strength of gravity from the star at the planet's position amounts to about 8,000 times Earth's surface gravity from the Sun. A pull that keeps the planet locked in its tight 1.1-day orbit and creates the tidal forces that distort the planet's shape. The star's mass and the planet's distance from it determine the orbital period through Kepler's laws, the same mathematical relationships that govern all orbital motion. The star rotates slowly, taking about 40 days to complete one rotation on its axis, much slower than the planet's 1.1-day orbital period. This difference in rotation rates matters. For the tidal interactions, the planet orbits faster than the star rotates, which creates a situation where tidal bulges raised on the star by the planet lag behind the planet's position. This lag creates a gravitational torque that transfers angular momentum from the planet's orbit to the star's rotation, slowly speeding up the star's spin while simultaneously slowing down the planet's orbit and causing it to spiral inward. The slow rotation of the star also indicates that the star has not been significantly spun up by tidal interactions yet, suggesting either that the planet has not been in this close orbit for very long, or that other factors limit how fast the star can rotate. The star shows no signs of unusual activity beyond what would be expected for a star of its type and age. No extreme flaring or variability that would indicate magnetic field complications or other stellar pathologies. Observations reveal modest star spot activity, dark regions on the star's surface where magnetic fields suppress convection and cool the surface locally, similar to sunspots on our sun. These star spots rotate with the star, creating small variations in the star's brightness as the spotted regions rotate into and out of view. And careful monitoring of these variations helps astronomers determine the star's rotation period and orientation. The star's magnetic field, generated by convection and rotation in its interior, extends outward into space and interacts with the charged particles in the planet's atmosphere, creating electromagnetic connections between star and planet. The star contains nuclear fusion reactions in its core, where hydrogen nuclei overcome their electrical repulsion through the heat and pressure at the center and combine to form helium, releasing energy according to Einstein's mass-energy equivalence. The core temperature reaches about 16 million degrees Kelvin, hot enough for protons to fuse, and the pressure at the core amounts to hundreds of billions of times Earth's atmospheric pressure, crushing the hydrogen into a dense plasma. The fusion reactions release energy in the form of gamma-ray photons that begin a long journey outward through the star's interior, bouncing through the dense material, gradually losing energy and shifting to longer wavelengths, taking hundreds of thousands of years to reach the surface, where they finally escape into space as visible light and heat. The star will outlive its planet by billions of years, continuing to burn hydrogen long after WASP-12b has spiraled inward and been destroyed. In about 3 to 4 billion years, the star will exhaust the hydrogen in its core and begin expanding into a red giant, growing larger and cooler at the surface, perhaps swelling to hundreds of times its current radius. If any planets remain in more distant orbits, they might survive this red giant phase, though they will be scorched by the increased luminosity and possibly engulfed if the star expands far enough. Eventually, the star will shed its outer layers as a planetary nebula and settle into a white dwarf, a dense, Earth-sized remnant that will cool slowly for trillions of years. But these distant future stages have no bearing on WASP-12b, which will be gone long before the star begins its evolution off the main sequence. The star is not evil or cruel. It has no awareness or intention. It simply exists and operates according to the laws of physics that govern stellar behavior. The star's gravity and radiation create the conditions that doom WASP-12b. But the star does not act with purpose. It merely responds to the presence of mass nearby, exerting gravitational force according to Newton's and Einstein's equations. The destruction of the planet arises not from the star doing anything unusual, but from the planet being in the wrong place, too close to survive the normal operation of stellar gravity and radiation. If the planet orbited farther away, at Earth's distance or Jupiter's distance, it would be perfectly safe. A normal gas giant enjoying billions of years of stable existence. But at 3.4 million kilometers, the proximity makes survival impossible. The star gains mass from the planet as material escapes the planet's atmosphere and falls toward the star, though the amount is trivial compared to the star's total mass. The planet loses about 6 million tons per second, which amounts to about 200 trillion tons per year, a staggering number in human terms, but tiny compared to stellar scales. The star contains about 2.8 times 10 to the 30th power kilograms of mass, more than 1 million times more massive than the planet. So, even if the planet transferred all its mass to the star, it would increase the star's mass by only a tiny fraction of a percent. The material falling onto the star mixes into the outer convective layers and eventually gets pulled into the core, where it participates in fusion, becoming helium and releasing energy. The planet's atoms transformed into stellar fuel. Observing the star from a distance, you would see nothing unusual. Just a normal yellow-white star shining steadily, indistinguishable from millions of others in the galaxy. Only by detecting the planet through transits or measuring the star's slight wobble due to the planet's gravitational pull would you realize that something interesting happens here. The star appears in the constellation Auriga, as seen from Earth, located about 1,400 light-years away, far enough that the star remains invisible to the naked eye from Earth's surface, despite being similar to our Sun. Telescopes can see it easily, and the star has been catalogued and studied, revealing its properties and the presence of its doomed planet through years of careful observation. The star's light takes 1,400 years to reach Earth, traveling across the immense gulf of interstellar space at the speed of light, meaning we see the star and its planet as they were 1,400 years ago, when that light began its journey. The planet's doom plays out on timescales of millions of years, so 1,400 years makes little difference. The planet was doomed then and remains doomed now, and will be doomed for millions of years into the future, until the final destruction arrives. The light arriving at Earth tonight left the star during the early medieval period by human reckoning. Yet, for the star and planet, nothing has changed. They continue their ancient dance just as they do today, time passing slowly on cosmic scales. The star WASP-12 serves as both the planet's gravitational anchor and its destruction, the object that holds the planet in orbit while simultaneously pulling it toward dissolution. Understanding the star helps us understand the planet's fate. The stellar mass determines the strength of gravity and tidal forces. The stellar radiation creates the heat that expands the planet's atmosphere. The stellar activity influences the rate at which the planet loses mass. The star is ordinary unremarkable, and yet its proximity to a massive planet creates an extraordinary situation. A cosmic event that demonstrates the diversity of outcomes possible in planetary systems. The star will continue shining long after its planet is gone. Indifferent to the loss, a stellar furnace burning through its fuel supply, with no awareness of what it has destroyed. The relationship between star and planet in this system is not one of predator and prey, or parent and child, but simply one of mass and gravity operating according to physical laws. The planet happened to orbit too close, whether through migration or through an unlikely close formation. And physics dictates what happens next. The star exerts gravitational force. The planet responds by deforming and losing mass. Orbital mechanics causes the orbit to decay, and eventually the planet will cross the Roche limit and disintegrate. The star does not consume the planet through any active process. Instead, the planet falls into the star through the inexorable operation of orbital decay, pulled inward by the same tidal forces that distort its shape. And this inward spiral brings us to the death spiral itself, the gradual decay of the orbit that seals the planet's fate. The orbit of WASP-12b is not stable, and measurements taken over years reveal that the planet arrives at its transits slightly earlier than it should if the orbit were constant. Each time the planet crosses in front of its star as viewed from Earth, the event occurs about 10 milliseconds earlier than predicted, based on a perfectly stable orbit, a tiny shift that accumulates over many orbits into a measurable and undeniable signal. 10 milliseconds per year sounds like nothing, an imperceptible change, yet this tiny difference reveals something profound happening in the system. The planet's orbit is decaying, shrinking, bringing the planet closer to its star with each passing year. This orbital decay, this death spiral, guarantees the planet's eventual destruction more certainly than the atmospheric loss or the tidal distortion. The measurements that detected this orbital decay required exceptional precision, tracking the timing of transits to an accuracy of a few seconds over a baseline of many years. Astronomers began observing WASP-12b shortly after its discovery in 2008, recording each transit, noting the exact moment when the planet began crossing the star's disk and when it completed the crossing. These observations accumulated over more than a decade, creating a dataset spanning thousands of orbits. And when astronomers compared the observed transit times to predictions based on a constant orbital period, they found a systematic pattern. The transits arrived early, not randomly but consistently, with the offset growing larger over time, indicating that the orbital period was decreasing at a steady rate. The cause of this orbital decay lies in tidal interactions between the planet and the star. The same tidal forces that distort the planet's shape also affect the orbit itself through a mechanism involving energy dissipation. The planet raises tides on the star, creating bulges in the star's surface, analogous to the tides our moon raises on Earth's oceans. And these stellar tides contain energy that dissipates as heat through friction in the star's interior. This dissipation removes energy from the system, and since the orbital energy determines the size of the orbit through Kepler's laws, removing energy causes the orbit to shrink. The planet moves slightly closer to the star each orbit. The orbital period decreases fractionally, and the gap continues to close in a slow but accelerating spiral. The 10 milliseconds per year decay rate translates to the planet moving closer to the star by about 75 centimeters per year, less than a meter annually, a pace that seems glacially slow by human standards. Yet this pace continues relentlessly, year after year, and over millions of years the accumulated change becomes enormous, the orbit shrinking by hundreds of thousands of kilometers, bringing the planet from its current position at 3.4 million kilometers to ever closer proximity. The decay accelerates as the orbit shrinks, because tidal forces strengthen rapidly as distance decreases, following an inverse cube relationship that makes tidal forces 8 times stronger if you halve the distance. So, as the planet spirals inward, the decay rate increases, creating a positive feedback loop that hastens the final destruction. Orbital mechanics follows precise mathematical laws discovered by Kepler and Newton and refined by Einstein, and these laws dictate how orbital period relates to orbital distance. A planet in a circular orbit has an orbital period determined by the semi-major axis of the orbit and the mass of the central star, with longer orbits having longer periods and shorter orbits having shorter periods. When tidal dissipation removes energy from the orbit shrinks and the period decreases accordingly. The planet orbiting faster as it moves closer, because it must move faster to maintain orbit at the smaller radius. This creates the observed effect, the transits arriving earlier than predicted, because the orbital period has decreased since earlier observations. The time remaining until the planet's destruction can be estimated from the decay rate, though the estimate carries uncertainty because the decay accelerates as the planet approaches closer. Current models suggest the planet has about 3 to 3.5 million years remaining before it reaches the Roche limit and begins to disintegrate, a time span short by cosmic standards, but longer than human civilization has existed. 3 million years from now, no human will witness the planet's final days unless humanity survives and maintains technological civilization for periods comparable to the entire history of human evolution. And even if we do survive that long, the event will take centuries or millennia to fully unfold as the planet slowly tears apart and its debris spirals into the star. The uncertainty in the 3 million year estimate arises from uncertainties in how efficiently the star dissipates tidal energy, and from uncertainties in the exact Roche limit distance, which depends on the planet's internal structure and density distribution. If the star dissipates tidal energy more efficiently than models predict, the decay could happen faster, if less efficiently, slower. If the planet has a dense core that can survive closer approaches, the final destruction might be delayed. If the planet is uniform gas and liquid all the way through, destruction might come sooner. These unknowns make precise prediction impossible, but the general timeline of a few million years appears robust across different models and assumptions. The planet has already passed the point of no return. There is no mechanism that could save it from its fate, no orbital resonance or planetary migration that could push it back out to a safer distance. The tidal forces that cause the decay will only strengthen as the planet approaches closer, and no counteracting force exists to halt or reverse the spiral. Atmospheric loss alone would not doom the planet on short timescales. Even losing 6 million tons per second, the planet could persist for billions of years if the orbit remained stable. But the orbital decay ensures destruction within a few million years regardless of atmospheric loss, making the planet's doom certain and the timeline relatively short by astronomical standards. Other planets in the system, if any exist, will be unaffected by WASP-12b's demise. They orbit farther from the star, where conditions allow stable long-term existence. And the destruction of one planet does not threaten others at safe distances. Observations have not detected additional planets in the WASP-12 system, suggesting WASP-12b might be alone, though planets farther out would be harder to detect through transits if their orbital planes did not align perfectly with our line of sight from Earth. The migration process that brought WASP-12b so close might have disrupted or ejected other planets during the system's early history, or the planet might have formed alone in a sparse protoplanetary disk. We cannot know from current observations. The decay rate of 10 milliseconds per year represents a balance between the tidal forces trying to slow the planet down and the planet's inertia trying to maintain its orbit, with the tidal forces slowly winning the battle. As the planet orbits, it raises tides on the star that lag behind the planet's position due to the star's slower rotation. And these lagging tides exert a gravitational pull on the planet that opposes its orbital motion, acting like a gentle brake that gradually removes orbital energy. The braking effect is weak, only about 10 parts per billion per orbit, but it operates continuously and never ceases, accumulating changes that add up to observable effects over years and to dramatic changes over millions of years. The orbit will continue to decay until the planet reaches the Roche limit, the critical distance where tidal forces equal the planet's own gravitational binding. And once the planet crosses into the Roche limit region, the destruction begins in earnest. The current distance of about 3.4 million kilometers places the planet outside the Roche limit, but close enough that tidal effects are already significant. Hence the egg shape and the atmospheric loss. The Roche limit for WASP-12b sits at perhaps 3 million kilometers based on the planet's density, giving the planet about 400,000 kilometers of room, a buffer that will be consumed over the next few million years as the decay continues. The final stages of the orbital decay will proceed rapidly once the planet approaches within a few percent of the Roche limit, the tidal forces increasing dramatically, and the decay rate accelerating from meters per year to kilometers per year or more. Models suggest the final approach might take only tens of thousands of years once the planet comes within a few hundred kilometers of the Roche limit. A rapid collapse compared to the millions of years of gradual decay that preceded it. During this final phase, observers with sufficiently sensitive instruments could watch the orbit change noticeably within a human lifetime, the transits arriving minutes or even hours earlier, year by year, as the planet's doom accelerates toward its conclusion. The inevitability of the orbital decay gives WASP-12b a certain tragic quality. The planet is doomed and knows no escape, its fate written in the mathematics of orbital mechanics and tidal dissipation. The planet cannot avoid its destruction, any more than a dropped object can avoid falling to the ground. Gravity and physics determine what happens next, and no force can intervene. Yet, from the planet's perspective, if inanimate objects could have perspectives, the doom might seem distant. 3 million years is an eternity compared to human timescales, longer than primates have existed on Earth, and the planet continues its existence day by day, orbit by orbit, slowly approaching the end, but still present and real for now. Watching the planet from your position in space, the orbital decay is not visible on human timescales. The planet's position looks the same today as it will tomorrow. or next year, or even a century from now. Only instruments with atomic clock precision timing the transits over years can detect the tiny shifts that reveal the decay, the change too slow for direct visual observation over any reasonable period. Yet knowing the decay occurs changes how you see the planet. The doomed world spiraling inward, invisibly, each orbit bringing it fractionally closer to the star. The death spiral, proceeding with the patience of cosmic time, unstoppable and inevitable despite being imperceptible to the eye. The planet's mass loss through atmospheric escape and its orbital decay are separate processes, though they interact in subtle ways. The atmospheric loss reduces the planet's mass, which slightly weakens its gravitational effect on the star, while the orbital decay brings the planet closer, which strengthens tidal forces and may increase the rate of atmospheric loss. These processes feed on each other, creating a complex interplay where the destruction accelerates as it proceeds. Though the timescales remain dominated by the orbital decay, which will cause final destruction millions of years before atmospheric loss alone would strip the planet entirely. The planet is dying from two causes simultaneously: losing its atmosphere to space while spiraling toward its star, and both processes contribute to the overall doom, though orbital decay seals the fate more quickly. As the planet spirals inward over the coming millions of years, its atmosphere will respond to the changing conditions, the increasing heat as the distance closes, and the strengthening tidal forces as the Roche limit approaches. The atmospheric loss rate will increase, the egg-shaped distortion will become more extreme, and the planet's structure will become increasingly unstable as the forces trying to tear it apart grow stronger, while the planet's ability to resist them weakens through mass loss and density reduction. The final million years will see dramatic changes in the planet's appearance and behavior, leading to the ultimate destruction that awaits when the tidal forces finally overcome the planet's structural integrity. And understanding what that final destruction will look like requires exploring how planets disintegrate when they cross into the Roche limit. What happens when a world finally comes apart under tidal stress? The atmosphere of WASP-12b extends far beyond what you might expect from a normal gas giant planet, reaching outward from the planetary body in a huge diffuse cloud that surrounds the planet for tens of thousands of kilometers in all directions. This extended atmosphere consists of hydrogen and helium heated to extreme temperatures by the nearby star's radiation. The gas so hot that it expands vigorously, puffing outward until the planet's weak gravity can barely hold on to it. The boundary between the planet and space becomes blurred in this extended envelope. No clear surface exists where the atmosphere ends. Instead, the density gradually decreases with altitude until it fades into the near vacuum of interplanetary space. Material from the upper reaches of this extended atmosphere escapes the planet's gravity entirely, flowing away into space at a rate measured in millions of tons per second. 6 million tons of material leave the planet every second, escaping the gravitational pull and drifting away from WASP-12b into the surrounding space. This mass loss rate, while enormous by human standards, represents only a tiny fraction of the planet's total mass. About 200 trillion tons per year from a planet whose total mass amounts to roughly 6 times 10 to the 27th power kilograms. At this rate, the planet could theoretically survive for trillions of years before losing all its mass through atmospheric escape alone. But the planet does not have trillions of years, or even billions. The orbital decay will destroy it within a few million years, long before atmospheric loss could strip it entirely. Yet the atmospheric escape matters because it reveals the extreme conditions affecting the planet, and because some of the escaping material falls toward the star, creating a connection between planet and star. The escaping material creates a tail behind the planet, analogous to a comet's tail. As the planet moves through its orbit, the gas flowing away from the planet encounters the star's radiation pressure and the stellar wind, a stream of charged particles flowing outward from the star. And these forces push some of the escaping gas away from the planet in the direction opposite the star. As the planet orbits, this tail of gas streams behind it, creating an elongated cloud of material that extends for hundreds of thousands of kilometers along the planet's orbital path. Observations from Earth using transit spectroscopy can detect this tail because it absorbs starlight over a longer period than the planet's solid body alone would cover, extending the transit duration and allowing astronomers to infer the presence of the extended escaping atmosphere. Spectroscopy reveals what elements exist in the escaping atmosphere. Ultraviolet observations showing absorption lines from metals that should not exist in gaseous form at the temperatures present in the outer atmosphere of a normal gas giant. Magnesium and calcium appear in ionized form, having lost one or more electrons due to the intense ultraviolet radiation from the star. And these ions absorb starlight at specific wavelengths, creating dark lines in the star's spectrum when the planet transits. The presence of these metals indicates how thoroughly the extreme heat has disrupted the planet's atmospheric structure, preventing the usual process where heavier elements sink toward deeper layers and lighter elements, like hydrogen and helium, dominate the upper atmosphere. The planet's day side, the hemisphere permanently facing the star due to tidal locking, receives the full brunt of the star's radiation and heats to temperatures around 2,500 degrees Celsius. At these temperatures, rock would glow red hot and many materials would melt, though the gaseous atmosphere has no solid surface to melt. The heat causes the atmospheric gas to expand enormously, the thermal energy making the atoms and molecules move rapidly and push outward against the planet's gravity. This thermal expansion reduces the atmosphere's density and increases its scale height, the altitude over which atmospheric pressure drops by a factor of E, creating the extended, puffed-up structure that makes the planet vulnerable to both atmospheric escape and tidal forces. The night side, the hemisphere permanently facing away from the star, remains much cooler, though still hot by any reasonable standard for a planet, maintaining temperatures around 1,100 degrees Celsius. Heat flows from the hot day side to the cooler night side through atmospheric circulation, powerful winds carrying energy around the planet at speeds that might reach thousands of kilometers per hour. Despite this heat transport, the temperature difference between day and night sides remains substantial, over 1,000 degrees, creating dramatic weather systems and violent atmospheric dynamics as the heated gas on the day side rises and flows toward the night side, while cooler gas from the night side flows back toward the day side to replace it. The mechanism of atmospheric escape involves several processes working together to lift gas out of the planet's gravitational well. Thermal escape occurs when individual atoms or molecules in the upper atmosphere move fast enough to exceed the escape velocity. about 60 kilometers per second, for this planet, and fly off into space rather than falling back down. Hydrodynamic escape occurs when the lower atmosphere heats and expands so vigorously that it pushes the upper atmosphere outward in a bulk flow, carrying material to high altitudes where it can more easily escape. Photoevaporation occurs when energetic ultraviolet photons from the star ionize atoms in the upper atmosphere, giving them additional energy and removing electrons that might have held them in molecules, making escape easier. The tidal forces that distort the planet's shape also contribute to atmospheric loss by stretching the atmosphere outward, toward, and away from the star, creating regions at the tips of the egg-shaped planet, where the effective gravity becomes very weak. At the substellar point, the location closest to the star, material experiences both outward tidal force pulling toward the star and centrifugal force from the planet's rapid rotation. And these forces partially cancel the planet's gravitational pull, allowing thermal expansion to lift material to great heights where it can escape. Similarly, at the antistellar point, the far side of the planet, tidal effects reduce the effective gravity, though to a lesser degree than at the substellar point. The escaping material does not all drift away into interstellar space. Some of it falls toward the star, drawn by the star's much stronger gravitational pull once the gas escapes the planet's Hill sphere, the region around the planet where the planet's gravity dominates over the stars. An accretion stream forms, a flow of gas from the planet toward the star, visible in some observations as absorption of starlight by the flowing material. This stream carries metal-enriched gas from the planet's atmosphere to the star's surface, where it impacts and merges with the star's outer layers. The star gains this material at the planet's expense, literally consuming the planet's substance, though the amount remains trivial compared to the star's enormous mass. The extended atmosphere and the material it contains change how the planet appears during transits, as observed from Earth. The planet blocks more light than its nominal radius would suggest, because the extended atmosphere absorbs starlight over a larger area than the planet's body. The transit depth, the fraction of starlight blocked during transit, is greater than what the planet's size alone would cause, indicating the presence of atmospheric material extending well beyond the planet's normal boundaries. Observations at different wavelengths reveal different transit depths, with ultraviolet observations showing deeper transits due to absorption by ionized metals in the extended atmosphere, while infrared observations show shallower transits closer to what the planet's body alone would produce. The atmospheric circulation patterns on WASP-12b likely create complex and violent weather. The extreme temperature gradients driving winds and atmospheric flows, unlike anything in our solar system. The substellar point, where the star's heat concentrates most intensely, may host a permanent storm or superheated region, where atmospheric temperatures peak and where material rises rapidly in a huge, convective updraft. This rising material flows outward toward the terminator, the boundary between day and night sides, where it cools somewhat and descends before flowing back toward the substellar point, creating a circulation cell that redistributes heat around the planet. Turbulence and instabilities in this flow create storm systems and eddies that churn the atmosphere continuously. The composition of the atmosphere consists primarily of hydrogen and helium, in roughly the same 3-to-1 ratio by mass, that these elements exist throughout the universe. Hydrogen being by far the most abundant element, and helium second. Trace amounts of heavier elements exist mixed into the atmosphere, carbon and oxygen, in the form of carbon monoxide or carbon dioxide possibly, nitrogen, and the metals like magnesium, calcium, and iron detected through spectroscopy. Water might exist deep in the atmosphere where temperatures drop below the dissociation point, and pressure remains high enough to hold molecules together. Though at the extreme temperatures of the upper atmosphere, water molecules would break apart into hydrogen and oxygen and exist only as atoms or ions. The planet's thermal emission, the heat it radiates into space from its hot atmosphere, makes it glow faintly in infrared wavelengths, contributing to the planet's visibility beyond just reflected starlight. Observations with infrared telescopes can detect this thermal emission, measuring how much heat the planet radiates and learning about the temperature distribution across the planet's surface. The day side emits far more infrared than the night side, creating a variation in the total thermal emission as the planet orbits and shows different faces toward Earth. This variation allowing astronomers to map the planet's temperature and study its atmospheric circulation without needing to resolve the planet's disk visually. The loss of atmosphere continues day by day, year by year, slowly reducing the planet's total mass and slightly changing its size and density as the outer layers evaporate. Though the changes occur so gradually that they would be difficult to measure over human timescales. Over millions of years, the cumulative effect could be significant, the planet losing perhaps a few percent of its mass to atmospheric escape before the orbital decay brings it to destruction. This mass loss slightly accelerates the orbital decay because reducing the planet's mass weakens its gravitational effect on the star, slightly altering the tidal interactions, though the effect is small compared to the ongoing tidal dissipation. The escaping atmosphere of WASP-12b provides a window into understanding how planets lose mass in extreme environments. Processes relevant not just to this one doomed world, but to many other hot Jupiter planets and to the evolution of close-in exoplanets generally. Planets closer to their stars experience stronger radiation and heating that can drive atmospheric escape, and understanding the mechanisms and rates of this escape helps astronomers predict which planets might be stable and which might be slowly evaporating away. WASP-12b serves as an extreme example, a laboratory where atmospheric loss proceeds rapidly enough to measure and study in detail, revealing principles that apply more subtly to less extreme planets. Viewing the planet from a distance, you might not see the atmospheric escape directly. The escaping material is too diffuse and too faint to be visible against the glare of the nearby star. But instruments detecting ultraviolet light can see the absorption from the escaping metals, the shadow they cast when the planet transits, revealing the extended cloud of gas surrounding the planet. Infrared instruments can map the temperature differences across the planet, showing how the day side radiates heat while the night side remains relatively cooler. Spectroscopic instruments can identify which elements exist in the atmosphere and whether those elements are neutral or ionized, revealing the chemical and physical state of the gas being stripped away. Together, these observations build a picture of a planet hemorrhaging its atmosphere into space, losing millions of tons every second in a slow dissolution that contributes to the planet's ultimate fate. The atmosphere that remains bound to the planet continues to be heated by the star, continues to expand and puff up the planet's size, continues to flow in circulation patterns from day side to night side and back, a dynamic system persisting even as it slowly dissipates. The planet's atmospheric structure adjusts continuously to the balance between heating from the star, heat transport by circulation, radiative cooling to space, and mass loss through escape. This balance determines the planet's size, density, temperature profile, and the rate at which it loses mass, all interconnected through the physics of atmospheres under extreme radiation. The extended atmosphere, the escaping material, the thermal glow, and the absorption signatures during transit all tell the story of a world being stripped of its substance, slowly consumed by the combination of stellar heat and gravity. And this atmospheric loss combines with the orbital decay and tidal distortion to create the complex process of planetary death that will culminate in the final fate awaiting WASP-12b. The future of WASP-12b is written in the physics of tidal forces and orbital mechanics, a timeline stretching about 3 million years into the future before the planet reaches the end of its existence. 3 million years from now, if current understanding of the decay rate proves correct, the planet will have spiraled inward to the point where it crosses fully into its Roche limit. And when that happens, the gentle atmospheric loss and slow orbital decay will give way to a more rapid and dramatic disintegration. The planet's structure, already stretched into an egg shape by tidal forces, will elongate even further as the distance to the star decreases and the tidal forces strengthen, the egg becoming more extreme until the material at the tips of the elongated planet can no longer remain gravitationally bound to the body. The disintegration will not happen as a sudden explosion. Planetary destruction through tidal forces proceeds through gradual stripping rather than catastrophic detonation. Material pulled away from the planet in streams and filaments, rather than the entire world blowing apart in one moment. The planet will begin to shed material from the points nearest and farthest from the star, the tips of the egg where tidal forces are strongest and where the planet's gravitational binding is weakest. Gas, and possibly liquid from the planet's outer layers, will flow away from these points in continuous streams, like water pouring from opened valves, material escaping the planet's gravity and forming bridges of gas, connecting the planet to the surrounding space. These streams will spiral around the star, spreading into an irregular ring or torus of debris orbiting where the planet used to be. As the planet loses mass from its extremities, its structure will become increasingly unstable, the remaining mass concentrating toward the center, while the outer layers stream away, perhaps revealing deeper layers or a core, if one exists. If WASP-12b has a rocky or icy core at its center, something denser than the surrounding hydrogen and helium atmosphere, this core might survive for some time after the outer layers are stripped, orbiting the star as a super-Earth-sized remnant, slowly losing altitude as its own orbital decay continues. Eventually, even a core would cross the Roche limit for its density, which for rock is closer to the star than for gaseous hydrogen, and the core would begin to break apart as well, tidal forces fracturing it into smaller pieces that continue orbiting and gradually spiraling inward. The debris from the disintegrated planet will form a ring around the star, an irregular collection of gas and possibly solid chunks spread along the planet's former orbital path, circling the star in the same direction the planet orbited, but now as separated fragments rather than a coherent body. This ring will be chaotic and short-lived, the particles within it colliding with each other, some fragments gaining energy and moving to higher orbits, while others lose energy and spiral inward toward the star. The tidal forces and the star's radiation will continue affecting the debris, heating the gas and dust, pushing material inward or outward, depending on size and composition, sorting the ring into different components based on the physics affecting each type of material. Over time, perhaps tens of thousands of years after the initial breakup, the debris ring will gradually accrete onto the star, material spiraling inward and falling into the star's photosphere, where it merges with the star's outer layers. The star will experience a slow rain of material from the destroyed planet, the debris adding mass to the star, though the amount remains trivially small compared to the star's total mass. The star's surface might show temporary brightening or chemical composition changes if large amounts of material fall onto a small area, creating a hot spot or enriching the star's outer layers with heavier elements from the planet, though these effects would be subtle and might not even be detectable from Earth, depending on when they occur. Eventually, within perhaps 100,000 to a few 100,000 years after the initial breakup, the debris will be completely consumed. All the material from the planet either accreted onto the star or ejected from the system by close gravitational encounters with other objects. The system will return to a seemingly normal state, the star shining as it did before, no visible sign remaining that a planet once orbited here and was destroyed. Chemical analysis of the star's spectrum might reveal slightly enhanced abundances of elements like carbon or iron or calcium compared to stars that have never consumed a planet, providing the only evidence that something unusual happened in this system's history. A faint chemical fingerprint of planetary destruction recorded in the star's outer layers. The final phase of the planet's existence, from the moment it enters the rapid disintegration period until the last debris falls into the star, will likely span several thousand to perhaps tens of thousands of years, brief on cosmic timescales, but still far longer than human civilization has existed. If observers with advanced telescopes watched this destruction as it happened, they would see the planet shrinking in size over decades or centuries, its brightness during transits decreasing as its cross-section diminishes. And eventually, the transits would become irregular or cease entirely as the planet fragments into pieces, too small to block noticeable amounts of starlight. The system would transition from a planet-hosting star to a debris disk star to a normal star with no planetary companions in the inner system. The entire progression playing out over a time span comparable to the history of human cities and agriculture. No one from Earth will witness this destruction in real time. The event will occur in the far future, 3 million years from now, a time when humanity may or may not still exist, and certainly will not be recognizable in its current form. The planet itself will not know or care about its destruction, planets being inanimate collections of matter that follow physical laws without awareness or suffering. The destruction is not tragic in a moral sense, just the natural operation of physics applied to a planet in an untenable position, matter responding to gravity and tidal forces according to the equations that govern all objects in the universe. The planet's atoms will continue existing after the destruction, merged into the star, where they will participate in fusion reactions, some of them transformed into helium and energy, others remaining as heavier elements mixed into the star's substance. The process of planetary destruction through tidal forces has likely happened many times in the history of the galaxy. planets migrating too close to their stars and being torn apart, material from destroyed worlds adding to stellar masses and enriching stellar compositions. WASP-12b is not unique in being doomed. It is simply one example among potentially many others that have not yet been discovered or that have already been destroyed in the billions of years since the galaxy formed. Every close-orbiting hot Jupiter faces some risk of tidal destruction, depending on its exact distance, density, and the tidal strength of its star. And a fraction of these planets must occupy the dangerous zone where destruction becomes inevitable within cosmologically short times. The final image of WASP-12b before its destruction might show a highly elongated object stretched into a long ellipsoid, or even beginning to split into separate lobes, tidal forces having pulled the planet into a shape barely recognizable as a world. Material would stream from the ends of this elongated structure, invisible plumes or jets, the planet visibly dissolving as material escapes. The boundary between planet and debris becoming increasingly blurred. The color might shift as deeper layers become exposed, perhaps revealing different chemical compositions from the layers that once covered them. Or the entire object might glow from frictional heating as internal layers slide past each other under tidal stress. The object would look unstable, clearly in the process of coming apart, a world in its death throes. After the destruction, the star WASP-12 will continue its life, essentially unchanged, burning hydrogen in its core, shining steadily for billions more years before eventually exhausting its fuel and evolving into a red giant. The star will likely never host another planet in a close orbit, the conditions that brought WASP-12b to its doom being unlikely to repeat. Though the star might retain planets at larger distances, if any exist, or any survived the early dynamical evolution of the system. The star will carry within its outer layers a slight enrichment in heavy elements from the destroyed planet, a chemical memory of the world it consumed, though this enrichment will be buried beneath the star's enormous mass and might never be large enough to significantly affect the star's behavior or evolution. The destruction of WASP-12b represents the end point of a planetary migration that went too far, bringing a gas giant from the outer system where it formed to the inner system where conditions are incompatible with long-term survival. The planet's doom illustrates the dynamic nature of planetary systems, which can evolve and change over time through gravitational interactions and migrations, sometimes with destructive consequences. Understanding how and why planets like WASP-12b get into dangerous positions requires understanding planetary migration, how planets can move from their formation locations to very different orbits through interactions with disks or other planets, a process that shapes planetary system architecture throughout the galaxy and determines which planets survive and which are doomed. But before exploring migration, we should first recognize that WASP-12b is not alone in its fate. Other planets have been discovered facing similar doom, other worlds spiraling toward their stars, or already being consumed. And among these doomed worlds, another stands out as a particularly interesting case. The planet that holds the distinction of being the very first exoplanet candidate the Kepler mission ever detected. A world that took years to confirm and that turned out to also be doomed to destruction. WASP-12b belongs to a category of exoplanets called hot Jupiters, gas giant planets, orbiting extremely close to their stars, closer than Mercury orbits our Sun. Their proximity creating temperatures and conditions unlike anything in our solar system. Hundreds of hot Jupiters have been discovered since the first one. 51 Pegasi b was found in 1995. And these planets have transformed our understanding of planetary systems and challenged the theories astronomers held about how planets form and where they can exist. Hot Jupiters orbit at distances ranging from about 0.01 to 0.1 astronomical units from their stars, completing orbits in periods from less than 1 day to about 10 days, racing around their suns at speeds of hundreds of kilometers per second. Their existence surprised astronomers who expected gas giants to form only in the cold outer regions of planetary systems, where ice and gas are abundant. Yet here, these massive planets sit, roasting in the intense radiation just above their stars' surfaces. The discovery of hot Jupiters revealed that planetary systems are far more diverse than we imagined from studying our solar system alone, where gas giants orbit at comfortable distances from the Sun, and rocky planets occupy the inner orbits. In hot Jupiter systems, the architecture is inverted, or at least disrupted, with massive planets where we expected only rock and metal. And this inversion tells us that planets can migrate, moving from their formation locations to very different orbits through processes that reshape entire planetary systems. Not all hot Jupiters are doomed. Many orbit at distances that allow stable existence for billions of years, despite the heat and proximity. The exact fate of each planet, depending on the balance between orbital distance, planetary density, stellar tidal strength, and other factors. Some hot Jupiters sit comfortably outside the dangerous zone, while others, like WASP-12b, exist on the edge or already inside the region where destruction becomes inevitable. The question of which hot Jupiters are doomed and which are safe depends on several factors that interact in complex ways to determine a planet's long-term survival. Orbital distance matters most obviously. Planets orbiting very close to their stars experience stronger tidal forces and more intense radiation heating that can puff up their atmospheres and make them vulnerable to both atmospheric loss and tidal disruption. Planetary density also matters. A dense planet with a rocky core resists tidal forces better than a puffy low-density planet like WASP-12b, able to orbit closer to the star without being torn apart. The star's tidal strength, which depends on the star's mass and how efficiently it dissipates tidal energy, determines how strongly the tidal interactions affect the planet's orbit, with some stars having stronger tidal effects than others, even at the same orbital distance. The rotation rate of the star influences the tidal interactions. Stars that rotate slowly relative to their planet's orbital periods create tidal forces that remove energy from the planet's orbit and cause inward migration, while stars rotating faster than the planet's orbit would theoretically add energy and push the planet outward, though this situation rarely occurs for hot Jupiters. The age of the system also plays a role. Younger systems might not have had time for significant tidal evolution to occur, while older systems have had billions of years for tidal effects to reshape orbits and potentially destroy planets. The combination of all these factors creates a spectrum of outcomes, from hot Jupiters that will orbit safely for billions of years, to those doomed to destruction within millions of years, to those that may already be disintegrating as we observe them. Scientists have identified several hot Jupiters that show signs of orbital decay similar to WASP-12b. Planets arriving at their transits earlier than predicted, based on constant orbits. The timing shifts, revealing that these worlds are spiraling toward their stars. The measurements require years of careful observation to accumulate enough data to detect the tiny changes in orbital period. And only a handful of planets have been observed long enough and with sufficient precision to confirm orbital decay. Each confirmed case adds to our understanding of how common planetary destruction is and what conditions lead to doom, helping astronomers predict which newly discovered hot Jupiters might be at risk and which are likely safe. WASP-18b orbits its star in less than 1 day at 0.02 astronomical units, even closer than WASP-12b. And this massive planet, containing more than 10 times Jupiter's mass, should theoretically experience rapid orbital decay. Yet observations have not definitively confirmed decay for WASP-18b, possibly because the planet's high mass and density make it more resistant to tidal effects. Or possibly because the star's tidal strength is weaker than expected, or simply because we have not observed long enough to detect the decay if it is happening slowly. The planet sits in a precarious position, close enough that destruction seems likely eventually, yet apparently stable for now, demonstrating how the balance of factors can create borderline cases where the outcome remains uncertain. WASP-19b completes an orbit around its star in less than 19 hours, one of the shortest orbital periods known for any hot Jupiter, placing it incredibly close to its star at just 0.016 astronomical units. This proximity subjects the planet to extreme heating and strong tidal forces, yet the planet appears to be surviving. Its relatively high density compared to WASP-12b, providing enough structural integrity to resist tidal disruption, at least for now. Whether WASP-19b will eventually succumb to orbital decay remains unknown. The planet has not been observed long enough to detect changes in its orbit, and its fate depends on factors we cannot yet measure precisely enough to predict with confidence. Some hot Jupiters show signs of ongoing atmospheric loss, their extended atmospheres detected through transit observations, revealing material escaping the planet's gravity and forming comet-like tails. Though atmospheric loss alone does not necessarily doom a planet, unless combined with other factors. The planet HD 209458b, also known as Kelt 9b, holds the record as the hottest known exoplanet, with dayside temperatures exceeding 4,000 degrees Celsius, hot enough to vaporize iron and most other metals. This extreme heat causes the planet's atmosphere to expand enormously and creates very high rates of atmospheric escape. Yet the planet's orbit appears stable, and the planet is not currently experiencing measurable orbital decay, demonstrating that heat and atmospheric loss alone do not guarantee doom if the orbital distance remains outside the tidal destruction zone. The variety of hot Jupiter outcomes reflects the variety of conditions under which these planets exist. Each system having its own unique combination of stellar and planetary properties that determine whether the planet survives or faces destruction. Some planets orbit stars that are just massive enough or just close enough to create the conditions for doom, while others orbit stars that are similar but with just enough difference to allow survival. The line between doomed and safe can be narrow. Small changes in orbital distance or planetary density shifting a planet from one category to the other. And this sensitivity to initial conditions means that predicting outcomes requires precise measurements and careful modeling. The discovery of multiple doomed hot Jupiters tells us that planetary destruction is not a rare or unusual occurrence. It happens throughout the galaxy, wherever planets migrate too close to their stars, a natural consequence of planetary system dynamics playing out over millions and billions of years. The fraction of hot Jupiters that are actually doomed remains uncertain. Current estimates suggest perhaps 1 to 5% of hot Jupiters orbit close enough to face destruction within a few million years, while the remaining 95 to 99% occupy orbits that allow survival for timescales comparable to their stars' lifetimes. Even if only a small percentage are doomed, the total number of hot Jupiters in the galaxy is large enough that many thousands or millions of planets must currently be in the process of being destroyed, each one following the same physical processes that affect WASP-12b. The study of doomed hot Jupiters provides insights into planetary migration and system evolution that would be difficult to obtain from studying stable planets alone. Doomed planets mark the endpoints of migration, the places where migration brought planets too close and sealed their fates. And by studying these endpoints, we can understand the migration processes better. The distribution of hot Jupiter orbital distances shows a pileup just outside the danger zone and a deficit very close to stars, consistent with the idea that migration brings many planets close, but that those brought too close are destroyed, leaving behind only the survivors at slightly larger distances. The doomed planets we observe now represent those caught in the process, not yet destroyed, but clearly on their way, giving us a window into dynamics that usually happen too slowly to observe. Hot Jupiters also teach us about the diversity of planetary systems in the galaxy, showing that our solar system's architecture, with gas giants in the outer system and rocky planets in the inner system, is not universal or even necessarily common. Many systems have giant planets close to their stars, where we have rocky planets, and some systems might have no planets at all in the inner regions if hot Jupiters or their migration disrupted or ejected everything else. Understanding hot Jupiters and their fates helps us understand what fraction of planetary systems might host Earth-like planets in stable orbits, and whether systems with hot Jupiters tend to have or lack other planets that might be habitable. The detection and study of hot Jupiters continues as new surveys discover more exoplanets and as long-term monitoring programs track known planets to detect orbital changes. Each new hot Jupiter discovered adds to the statistical sample, helping astronomers understand how common these planets are around different types of stars and at different orbital distances. Each confirmed case of orbital decay provides another data point for testing theories of tidal interactions and planetary migration, refining our models and improving our ability to predict which planets are at risk. The field continues to evolve as observations improve and as theoretical understanding deepens, revealing more about the complex processes that determine planetary fates. Among all the doomed hot Jupiters discovered and studied, one stands out for having a particularly interesting history of discovery. A planet that holds the distinction of being the very first planet candidate identified by NASA's Kepler mission in 2009. This planet, designated Kepler 1658b, took nearly a decade to confirm as a real planet rather than a false positive. And when it was finally confirmed in 2019, astronomers discovered something remarkable. The planet is not only real, but also doomed, experiencing orbital decay that will lead to its destruction in a few million years. The story of Kepler 1658b reveals how difficult exoplanet confirmation can be, and how some of the most interesting discoveries take years to fully understand. Kepler 1658b entered the astronomical record in 2009 as the very first planet candidate detected by the Kepler Space Telescope, a spacecraft launched specifically to find Earth-like planets around other stars by monitoring the brightness of thousands of stars simultaneously. The telescope detected a regular dimming of the star Kepler 1658 every 3.85 days, a pattern consistent with a planet crossing in front of the star and blocking a small fraction of its light. The planet candidate received the designation KOI-1, meaning Kepler Object of Interest Number 1. The first entry in what would eventually become a catalogue of thousands of planet candidates discovered by the mission. Yet, despite being first, this planet took longer to confirm than most others, a decade passing between initial detection and final confirmation. The delay arising from peculiarities in the system that made astronomers uncertain whether the signal represented a real planet or some other phenomenon. The star Kepler 1658 is not a sun-like dwarf star, but rather an evolved star that has begun moving off the main sequence, a subgiant star, larger and more luminous than it was during its main sequence lifetime. The star contains about 1.5 times the Sun's mass and has expanded to about 3 times the Sun's radius, making it substantially larger than the stars around which most known hot Jupiters orbit. This larger size created complications for confirming the planet, because the transit depth, the amount of light blocked during the planet's crossing, depends on the ratio of planet size to star size. And uncertainty about the star's exact size created uncertainty about whether the transiting object was truly planet-sized or something larger like a small star. The evolved nature of the star also made its properties harder to determine from observations. Stellar evolution theory predicting a range of possible sizes and temperatures for a star of this mass and age. Additional observations using radial velocity measurements, which detect the star's wobble caused by the planet's gravitational pull, eventually confirmed that the transiting object has a mass consistent with a giant planet rather than a star. The planet contains about 6 times Jupiter's mass, making it substantially more massive than typical hot Jupiters, and combines this high mass with a radius of about 1.5 times Jupiter's radius, giving it a density much higher than WASP-12b. The higher density makes Kepler 1658b more resistant to tidal disruption than the puffy low-density WASP-12b. Yet despite this resistance, the planet is still doomed, its orbit decaying measurably as tidal forces slowly drag it towards its star. The orbital decay of Kepler 1658b was discovered through the same method used for WASP-12b. Careful timing of transits over many years, revealing that the planet arrives at each transit earlier than predicted, based on a constant orbital period. The decay rate for Kepler 1658b measures about 22 milliseconds per year, more than twice the rate observed for WASP-12b, indicating faster orbital evolution and a shorter remaining lifetime. This faster decay occurs despite Kepler 1658b being denser and more resistant to tidal forces than WASP-12b, the higher decay rate arising from the star's properties rather than the planet's. The evolved subgiant star exerting stronger tidal forces than WASP-12b's main sequence star. Subgiant stars like Kepler 1658 have stronger tidal effects on their planets than main sequence stars of similar mass, because the evolutionary changes that create subgiants also affect their internal structure and rotation. As a star evolves off the main sequence and begins expanding into a subgiant, its core contracts and heats, while its outer envelope expands and cools. And these changes alter how efficiently the star dissipates tidal energy raised by orbiting planets. The expanding envelope increases the star's moment of inertia and slows its rotation, creating conditions where tidal interactions with close orbiting planets become stronger and more effective at removing energy from the planet's orbit. Additionally, the subgiant's larger radius means the planet orbits closer to the star's surface in terms of stellar radii, even though the actual distance in kilometers might be similar to other hot Jupiters, and this geometric factor enhances the tidal forces. The planet orbits at about 0.054 astronomical units from its star, farther than WASP-12b in absolute distance. Yet this distance represents only about 8 stellar radii for the expanded subgiant, compared to about 16 stellar radii for WASP-12b around its main sequence star. The closer approach in units of stellar radii means stronger tidal forces and faster orbital decay, demonstrating how the star's properties matter as much as the orbital distance when determining a planet's fate. Kepler 1658b experiences a gravitational environment that would be survivable around a main sequence star, but becomes deadly around an evolved subgiant. The planet's doom arising from the unfortunate combination of moderately close orbit and evolved host star. The estimated remaining lifetime for Kepler 1658b amounts to about 2.5 million years before the planet reaches its Roche limit and begins disintegrating, slightly shorter than WASP-12b's remaining 3 million years. The faster decay and shorter remaining lifetime mean that Kepler 1658b is closer to its end than WASP-12b is, this planet being farther along the path toward destruction. Over the next 2.5 million years, the planet will spiral inward, its orbital period decreasing, the tidal forces strengthening, the planet's egg-shaped distortion becoming more extreme, until finally, the structure fails and the planet begins to come apart. The discovery of orbital decay for Kepler 1658b came as a surprise when it was announced in 2019, a decade after the planet was first detected. The intervening years having provided enough baseline for the timing shifts to become measurable. The announcement made headlines because the planet was the first Kepler candidate, and because the confirmed orbital decay provided direct evidence of a planet in the process of being destroyed, a process predicted by theory but only recently confirmed through observation. Kepler 1658b joined WASP-12b as one of only a handful of planets with directly measured orbital decay. Each confirmed case valuable for testing theories about tidal interactions and planetary migration. The evolved state of the host star adds another dimension to the planet's doom, beyond just the orbital decay, because the star Kepler 1658 will continue evolving over the coming hundreds of millions of years, eventually expanding into a red giant. If the planet somehow survived the orbital decay, which it will not, the star's evolution would eventually consume it anyway. The red giant phase, bringing the star's surface outward to dozens or hundreds of times its current radius. The planet faces a dual threat. Orbital decay will destroy it in 2.5 million years, and stellar evolution would destroy it in perhaps 1 billion years, ensuring the planet has no possible escape from eventual destruction. The orbital decay will finish the job long before the stellar evolution does, making the star's future expansion irrelevant to this planet's fate. Observing Kepler 1658b provides an opportunity to study a doomed planet around an evolved star, a different environment from WASP-12b around its main sequence star, allowing comparisons that help astronomers understand how stellar properties affect planetary survival. The differences between the two systems, one with a main sequence star and one with a subgiant, and the similarities in their ultimate fates demonstrate that multiple paths lead to planetary destruction. Different combinations of stellar and planetary properties can all result in doom. The study of both systems together provides more complete understanding than either system alone could offer. The mass of Kepler 1658b, about 6 Jupiter masses, makes it one of the more massive hot Jupiters known, and this high mass creates stronger tidal forces on the star than a less massive planet would produce. The planet's gravity pulls on the star, raising tides in the star's body, and the star's rotation lag causes these tides to pull back on the planet, removing energy from the orbit. A more massive planet raises larger tides and therefore experiences stronger drag, accelerating the orbital decay. So in some sense, Kepler 1658b contributes to its own doom through its high mass, though the decay would occur for any planet in this position, just at different rates depending on mass. The density of Kepler 1658b, substantially higher than WASP-12b's density, means this planet is not puffed up by heat into a bloated structure. Instead, it maintains a more compact form despite the stellar radiation. The planet's atmosphere likely experiences heating and expansion similar to other hot Jupiters, but the planet's strong self-gravity prevents the extreme expansion that makes WASP-12b so vulnerable. Yet despite this structural advantage, the planet remains doomed, demonstrating that even dense planets cannot survive indefinitely at very close orbital distances around stars with strong tidal effects. The orbital decay proceeding regardless of planetary density once the orbit becomes close enough. The confirmation of Kepler 1658b as a planet and the discovery of its orbital decay came from work by astronomers who revisited the old Kepler data with new analysis techniques and combined it with new observations from ground-based telescopes. This detective work shows the value of archiving astronomical data. The original Kepler observations from 2009 becoming crucial years later for establishing the baseline needed to detect orbital decay. Without the long-time baseline provided by Kepler's early observations, detecting the decay would have required many more years of new observations to accumulate enough timing shifts to be measurable. The lesson is that some discoveries take patience and benefit from returning to old data with new insights. The story of Kepler 1658b, from first detection to decade-long limbo to final confirmation and discovery of its doom, illustrates how science sometimes progresses slowly. Some questions taking years to answer as data accumulates and techniques improve. The planet waited patiently in the catalogue as KOI-1, neither confirmed nor rejected, until enough information accumulated to determine its true nature. The fact that the first Kepler planet candidate turned out to be a doomed world adds a certain poetry to the mission's story, though the poetry is coincidental. The physical processes determining the planet's fate having nothing to do with human missions or priorities. Kepler 1658b orbits its star in the constellation Lyra, as seen from Earth, located about 2,700 light-years away, nearly twice as far as WASP-12b, and therefore more difficult to observe in detail. The greater distance means the star appears fainter from Earth, making follow-up observations more challenging, though still possible with large telescopes and sensitive instruments. The light we receive from this system left the star and planet about 2,700 years ago, showing us the system as it was during Earth's ancient history. Though on the timescales of planetary destruction, the 2,700-year difference between then and now makes no meaningful difference to the planet's fate. The planet's doom, like WASP-12b's, is certain and inexorable, the orbital decay proceeding according to physical law, the timeline counting down toward an end that will arrive in the future, whether anyone observes it or not. The planet will continue orbiting for millions of years, long enough that the event will not touch human civilization in any direct way, yet short enough that the planet's destruction is cosmologically imminent. Kepler 1658b and WASP-12b are not alone among doomed planets. They represent examples of a phenomenon that must occur throughout the galaxy, and beyond the hot Jupiters with measured orbital decay, other planets exist in even more extreme situations, orbiting so close to their stars that their very existence seems impossible. Some planets orbit their stars at distances so small and with periods so short that they barely seem possible. Worlds completing full orbits in less than one Earth day, racing around their suns at tremendous speeds in the tightest gravitational embraces known. These ultra-short period planets, defined as those with orbital periods less than 24 hours, push the limits of what planetary systems can create and maintain, existing in environments so extreme that survival seems improbable. Most ultra-short period planets are not gas giants, but rather rocky planets, super-Earths or mini-Neptunes that can withstand the tidal forces and radiation that would destroy a puffy gas giant at the same distance. The different composition allows these planets to orbit closer than hot Jupiters can, their higher density providing structural integrity that resists tidal disruption. WASP-19b completes an orbit around its star in just 18.9 hours, less than one Earth day, making it one of the shortest period gas giant planets known. The planet orbits at only 0.016 astronomical units from its star, about 2.4 million kilometers, even closer than WASP-12b. And this proximity subjects it to extreme tidal forces and temperatures exceeding 2,000 degrees Celsius. The planet's survival at such close range comes from its relatively high density, about half Jupiter's mass, packed into a volume only slightly larger than Jupiter, giving it enough structural strength to resist the tidal forces that would tear apart a less dense planet. Yet even this dense planet shows signs of stress. Its atmosphere is extended and evaporating, spectroscopic observations detecting material escaping from the planet. And while no orbital decay has been confirmed yet, the planet sits dangerously close to the edge. WASP-12b orbits its star every 22.5 hours at a distance of only 0.02 astronomical units. A massive planet containing more than 10 times Jupiter's mass in an extremely tight orbit. The planet's high mass creates correspondingly strong tidal forces on the star, and early studies suggested the planet might be experiencing rapid orbital decay. Predictions indicating the planet could be consumed within 1 million years. More recent observations have cast doubt on whether the decay is as fast as initially thought, measurements proving difficult due to the star's activity and the challenges of precise transit timing. But whether the decay is fast or slow, the planet's proximity to its star ensures it cannot survive indefinitely. Doom is certain even if the timeline remains uncertain. Rocky planets can orbit even closer than gas giants, because rock is far denser than hydrogen and helium gas, allowing rocky planets to resist tidal forces that would destroy gas giants at the same distance. K2137b, a rocky planet about 1.8 times Earth's size, orbits its star in just 10.7 hours, completing more than 2 orbits every Earth day. The planet sits at only 0.015 astronomical units from its star, so close that the star fills a substantial portion of the sky, as seen from the planet's surface, and temperatures on the day side likely exceed 1500 degrees Celsius, hot enough to melt rock. Despite these extreme conditions, the planet survives because its rocky composition gives it the density and structural strength to withstand the environment. The planet is essentially a ball of hot, molten rock orbiting just above its star's surface. Another remarkable ultra-short period planet, K2141b, orbits its star every 9.2 hours, completing nearly 3 orbits per Earth day. This planet also appears to be rocky based on its size and density, orbiting at about 0.013 astronomical units, where it receives intense stellar radiation that melts its surface and drives extreme weather patterns. The day side of such a planet would be molten, rock heated to liquid or gaseous states, while the night side might cool enough for rock to solidify, creating a world where rock evaporates on one hemisphere and rains down on the other, conditions utterly alien to anything in our solar system. These planets provide natural laboratories for studying matter under extreme conditions, temperatures, and pressures that we struggle to create even in experimental facilities on Earth. The shortest confirmed orbital period for any planet, as of current discoveries, belongs to K2137b at 10.7 hours. Though searches continue for planets with even shorter periods, the theoretical lower limit being somewhere around 4 to 6 hours, depending on the star's mass and the planet's composition. Below this limit, orbital mechanics and tidal forces make stable orbits impossible. Any planet that close would orbit faster than the star's surface rotates at the equator, creating conditions where tidal forces would immediately tear the planet apart, or where the orbit would intersect the star's photosphere, causing the planet to plow through the star's outer atmosphere and rapidly spiral inward. The ultra-short period planets we observe sit just outside this absolute limit, in a narrow zone where existence is possible, but precarious. Ultra-short period planets experience tidal locking. Their rotation synchronized with their orbit, so one face permanently points toward the star, while the other faces away into darkness. The same hemisphere, always receiving stellar radiation, while the other never sees the star. This creates extreme temperature differences between day and night sides, thousands of degrees separating the roasted day hemisphere from the relatively cooler night hemisphere. Though even the night side remains hot by Earth standards due to heat transport through the atmosphere or interior. On rocky planets, the heat might be carried by convection in the molten rock, or by conduction through the solid layers. While on gas giant ultra-short period planets, atmospheric circulation carries heat around the planet through fierce winds. The discovery of ultra-short period planets revealed that planetary systems can create and maintain configurations far more diverse than our solar system exhibits, showing that the range of possible planetary arrangements extends to extremes we had not anticipated. These planets likely formed much farther from their stars, in cooler regions where their materials could condense, and migrated inward through gravitational interactions or disk torques. The migration must have been dramatic, bringing planets from several astronomical units down to hundreds of an astronomical unit. A journey that may have destroyed other planets in the system or ejected them to interstellar space. The ultra-short period planets we see today are survivors of violent dynamical evolution, worlds that migrated inward but stopped just short of total destruction. Some ultra-short period planets orbit white dwarfs, stellar remnants, left after sun-like stars, exhaust their fuel and shed their outer layers. And these systems show that planets can sometimes survive even the death of their stars. WD 1856 plus 534b, a planet roughly the size of Jupiter, orbits a white dwarf every 34 hours at a distance of only 0.02 astronomical units. This planet somehow survived the red giant phase that the star went through before becoming a white dwarf, either because it migrated inward after the star shed its envelope, or because it was far enough away to avoid being engulfed during the red giant expansion. The planet's existence around a white dwarf proves that planetary systems can survive stellar evolution under some circumstances, though most close-in planets would be destroyed when their stars expand. The ultra-short period planets face different fates depending on their composition and orbital distance. Rocky planets generally surviving longer than gas giants at the same distance due to their higher density. For gas giant ultra-short period planets like WASP-12b and WASP-19b, the threat of orbital decay and eventual tidal disruption looms. These planets likely doomed on timescales of millions to tens of millions of years unless they orbit just far enough to be stable. Rocky, ultra-short period planets face threats from extreme heating and atmospheric loss, the intense stellar radiation possibly vaporizing their surfaces and stripping away any atmosphere. But the rocky cores themselves can potentially survive for billions of years if the orbital distance keeps them outside the Roche limit for rock. The study of ultra-short period planets helps astronomers understand the limits of planetary survival and the processes that determine where planets can exist. These extreme systems test our theories of planet formation, migration, and tidal evolution, providing examples of the most intense star-planet interactions possible. The planets serve as natural experiments, showing us what happens to matter under conditions of extreme heating, strong tidal forces, and rapid rotation. Conditions relevant to understanding not just exoplanets, but also the physics of matter more generally. Every discovery of an ultra-short period planet expands our knowledge of what is possible in the universe. The detection of ultra-short period planets requires precise photometry and timing, the transit durations being very short when the planet completes an orbit in less than a day, sometimes just an hour or two crossing in front of the star. Ground-based surveys can detect these planets, despite their short periods, the frequent transits actually making detection easier in some ways, multiple transits observable in a single night of observation. Space missions like Kepler and TESS have excelled at finding ultra-short period planets, their continuous monitoring allowing them to catch the brief transits and measure the periods precisely through observing many consecutive orbits. The question of how common ultra-short period planets are remains somewhat uncertain. They appear to be rare compared to planets with longer periods. Perhaps only 1 or 2% of stars host such planets, based on current surveys. The rarity makes sense given that reaching such close orbits requires special circumstances, significant migration, and fortunate timing to stop the migration before the planet is destroyed. Many planets that migrated inward probably did not stop in time and were consumed by their stars, leaving behind only the minority that managed to settle into stable, ultra-short period orbits. The planets we observe represent the lucky survivors, and for every ultra-short period planet that exists, many others may have been destroyed in the process of migration. Looking at these ultra-short period worlds from a distance, you would see planets moving visibly against their stars if you could resolve both objects. The rapid orbital motion, creating noticeable position changes over hours rather than days or weeks. A time-lapse video would show the planet whipping around its star at tremendous speed, the physics of orbital mechanics demanding high velocities for stable orbits at such small distances. These planets represent the extreme end of the spectrum of doomed and near-doomed worlds, some already experiencing orbital decay, others balanced precariously at the edge, all of them existing in environments where the margin between survival and destruction is razor-thin. And understanding how these planets reached their current positions requires exploring the migration processes that brought them so close to their stars. Planets do not form where we find hot Jupiters and ultra-short period planets. The regions very close to stars are too hot during planetary system formation for gas and ice to condense. Only refractory materials like rock and metal can exist in solid form that close. Gas giant planets, like Jupiter, form in the cooler outer regions of protoplanetary disks, beyond the frost line, where water freezes into ice, and where temperatures allow methane and ammonia to condense. The abundance of ice, providing the mass needed to build large, solid cores that can then attract enormous hydrogen and helium atmospheres. In our solar system, Jupiter formed at about 5 astronomical units from the Sun, Saturn at 9.5, and both remained roughly where they formed, migrating only modestly inward or outward over the solar system's history. The discovery of hot Jupiters at 0.05 astronomical units demanded explanation. How did these gas giants travel from their formation locations in the outer system to their current positions, hugging their stars? The answer is migration, the process by which planets move from their original orbits to new orbits through interactions with other objects, or with the disk of gas and dust from which they formed. Migration can occur through several different mechanisms, depending on the stage of the planetary system's evolution and the objects present, and understanding these mechanisms helps explain not just where planets end up, but also which planets are doomed and which are safe. The migration history of a planet determines whether it settles into a stable orbit or continues moving until it reaches the danger zone, where tidal forces will eventually destroy it, making migration history crucial to understanding the population of doomed worlds. Disk migration occurs early in a planetary system's history, while the protoplanetary disk of gas and dust still exists around the young star, typically within the first few million years after the star forms. A planet embedded in a disk interacts gravitationally with the disk material, the planet's gravity pulling on the gas and dust, while the gas and dust pull back on the planet. These interactions transfer angular momentum between the planet and the disk, and depending on the details of how the momentum transfer works, the planet can spiral inward toward the star or drift outward away from it. For massive planets like gas giants, the typical outcome is inward migration, the planet opening a gap in the disk and then following that gap as tidal forces from the disk cause both the gap and the planet to move inward over time. Type 1 migration affects lower mass planets that do not open gaps in the disk. These planets experiencing drag from the disk gas that causes them to spiral inward, sometimes rapidly on timescales of tens of thousands to hundreds of thousands of years. Type 2 migration affects massive planets that do open gaps, clearing the disk material near their orbits, and these planets migrate more slowly as they are coupled to the viscous evolution of the disk itself, timescales of hundreds of thousands to millions of years being typical. Both types of migration can bring planets very close to their stars, potentially into the zone where tidal effects become important, and some planets may migrate all the way into their stars and be destroyed during the disk phase. The migration stops when the disk dissipates, the gas and dust being blown away by the star's stellar wind or photo-evaporated by ultraviolet radiation from the star, or simply accreting onto the star or planets, typically after a few million years. Planets that have migrated inward during the disk phase end up wherever they were when the disk disappeared, if the migration brought them very close to the star and then stopped. They remain close indefinitely unless other processes move them again. Many hot Jupiters probably reach their current positions through disk migration, moving inward during the first million years of the system's history, and then becoming frozen in place once the disk was gone. Their orbital distances set by the interplay between migration rate and disk lifetime. High eccentricity migration offers an alternative pathway to create hot Jupiters, this process occurring after the disk has gone through gravitational interactions between planets. If two or more giant planets form in a system, they can gravitationally scatter each other through close encounters, one planet being flung outward into a wide eccentric orbit, or even ejected from the system entirely, while the other is thrown inward into a highly eccentric orbit that brings it very close to the star at its nearest approach. The planet on the eccentric orbit experiences strong tidal forces during its close approaches to the star, and these tidal forces gradually circularize the orbit, turning the elliptical path into a circular orbit at a distance close to the original perihelion, the closest approach point. This process creates a hot Jupiter from what was originally an outer system giant planet, no disk required. High eccentricity migration can be violent and destructive to other planets in the system. The gravitational scattering that initiates the process, often ejecting or destroying planets beyond just the two involved in the encounter. Systems with hot Jupiters created through this pathway are unlikely to have other planets in nearby orbits, the dynamical history having cleared out everything nearby, which matches observations showing that hot Jupiters tend to be lonely, with fewer close planetary companions than planets in longer period orbits. The circularization process takes time, millions to hundreds of millions of years, depending on the orbital parameters, giving the planet an extended period of eccentric oscillation before it settles into the final circular orbit. Some planets may migrate through secular interactions, long-term gravitational effects from other planets on more distant orbits that gradually change orbital eccentricities and inclinations over millions to billions of years. These secular effects can pump up a planet's eccentricity gradually, bringing it into closer approaches to the star until tidal circularization takes over and creates a hot Jupiter. This pathway is slower and subtler than high eccentricity migration through scattering, but it can operate in systems where direct scattering is unlikely, providing another route to creating close orbiting planets. The migration process determines where a planet ends up, and therefore whether it becomes doomed. Planets that migrate to 0.03 astronomical units might be safe for billions of years, while those that migrate to 0.02 astronomical units might be doomed to orbital decay within millions of years. The stopping point of migration depends on the details of the disk structure, the planet's mass, the presence of other planets, and essentially random factors in the chaotic evolution of young planetary systems. Some planets stop migrating at just the right distance to be stable, while others are less fortunate, ending up too close for long-term survival. The doomed hot Jupiters we observe are those that migrated too far inward, while the stable hot Jupiters migrated inward but stopped at safer distances. Migration explains why hot Jupiters exist and why some are doomed. But it also raises questions about what determines where migration stops and whether doomed planets could ever be saved, or whether their fates are sealed once migration brings them too close. In disk migration, the stopping point is often determined by the inner edge of the protoplanetary disk, a location where the disk material is cleared away by the star's magnetic field, or where the disk transitions from gas-dominated to magnetically dominated dynamics. Planets migrating inward can pile up at this inner edge, unable to migrate farther because there is no disk material beyond that point to interact with. If the inner disk edge sits at a safe distance, say 0.05 astronomical units, then planets stopping there might survive indefinitely. But if the inner edge sits very close to the star, planets stopping there might be doomed. In high eccentricity migration, the stopping point is determined by where the orbit circularizes, which depends on the original eccentricity and perihelion distance of the eccentric orbit. Essentially, random factors determined by the details of the scattering event. A planet that happens to scatter into an orbit with perihelion at 0.04 astronomical units will circularize there and might be safe, while one that scatters into an orbit with perihelion at 0.02 astronomical units will circularize there and probably be doomed. The randomness means that some planets win the lottery and end up safe, while others are not as lucky. Migration may continue even after the disk is gone through tidal interactions, though at much slower rates. The same tidal forces that cause orbital decay in doomed planets, also affecting planets at safer distances, just more weakly. A planet at 0.05 astronomical units might experience very slow tidal evolution that takes billions of years rather than millions, essentially stable on solar system timescales, but slowly changing on cosmic timescales. Over the lifetime of the host star, some planets, initially safe, might gradually migrate inward enough to enter the danger zone. Though this very slow migration is probably less important than the rapid early migration during the disk phase, or the sudden migration through scattering events. The migration history of our solar system's gas giants provides an interesting comparison to exoplanet migration. Jupiter and Saturn believed to have migrated somewhat during the solar system's early history, Jupiter moving inward and Saturn moving outward, until they became locked in a resonance that halted the migration. This migration may have been responsible for shaping the asteroid belt and possibly for delivering water to Earth and causing the late heavy bombardment of impacts about 4 billion years ago. Yet the migration was modest, Jupiter moving from perhaps 3.5 astronomical units to 5.2 astronomical units, where it sits today, never approaching close enough to the Sun to be at risk. Our solar system appears to have had a relatively calm migration history compared to systems with hot Jupiters. Understanding migration helps us understand the diversity of planetary systems and why some planets are doomed while others are safe. The migration process is fundamentally chaotic and sensitive to initial conditions. Small differences in disk properties or planetary masses, or the timing of interactions can lead to very different outcomes. This sensitivity means planetary system formation is not deterministic. We cannot predict exactly what configuration will result from a particular starting condition. Instead, there is a range of possible outcomes with different probabilities. Doomed planets represent one tail of the distribution, the unlucky outcomes where migration brought planets too close, while stable planetary systems, like our own, represent different parts of the distribution where migration was less extreme or stopped at safer distances. The migration models continue to be refined as more exoplanets are discovered and as our understanding of disk physics and planetary dynamics improves. Every new doomed planet discovered and every new stable hot Jupiter found provides data that helps test and improve the models. The field of planet migration is active and evolving, with debates about the relative importance of different migration mechanisms and about what factors control where migration stops. Doomed planets are particularly valuable for these studies because their positions and decay rates provide strong constraints on tidal physics and migration history, offering clues about how they arrived at their current doomed states. And discovering these doomed planets, measuring their orbital decay, and determining which planets are at risk all depend on patient observation and precise measurements that reveal the subtle signs of destruction. Detecting planets around other stars is challenging. The planets are small and dim compared to their bright host stars, and seeing them directly is nearly impossible, except in special cases. Most exoplanets are discovered through indirect methods that detect the planet's influence on its star, rather than seeing the planet itself. And the two most successful methods are the transit method and the radial velocity method. The transit method watches for periodic dimming of a star's brightness as a planet crosses in front of it, blocking a small fraction of the starlight, while the radial velocity method measures the star's wobble caused by the gravitational pull of orbiting planets. Both methods have discovered thousands of exoplanets, and both can detect signs of orbital decay in doomed planets, though detecting the decay requires long baselines of observation and exceptional precision. The Kepler Space Telescope, launched in 2009 and operating until 2018, revolutionized exoplanet discovery by monitoring more than 150,000 stars simultaneously, watching for the telltale dips in brightness that indicate planetary transits. Kepler discovered more than 2,700 confirmed planets and identified thousands more planet candidates awaiting confirmation, creating a statistical sample large enough to determine how common planets are around different types of stars and at different orbital distances. The mission found that planets are extremely common. Most stars host at least one planet, and many stars host multiple planets, showing that planetary system formation is a normal outcome of star formation. Among the thousands of planets Kepler discovered, several dozen are hot Jupiters, and a few of those show the signs of orbital decay. The TESS mission, the Transiting Exoplanet Survey satellite, launched in 2018, continues the transit search by surveying bright nearby stars across the entire sky, finding planets suitable for detailed follow-up observation. TESS focuses on bright stars because these allow precise measurements of transit timing and enable radial velocity follow-up with ground-based telescopes, creating opportunities to study planets in depth and to search for subtle effects, like orbital decay. TESS discovers dozens of new planets every year, including hot Jupiters and ultra-short period planets, some of which may turn out to be doomed when observed over sufficiently long baselines. Ground-based transit surveys like WASP, HAT, KELT, and others have also discovered hundreds of transiting planets by monitoring bright stars from networks of small telescopes distributed around the world. These surveys are less sensitive than space telescopes, but can monitor very bright stars that would saturate space telescope detectors. And they have discovered many of the best-studied hot Jupiters, including WASP-12b and WASP-18b. The ground-based surveys continue operating, adding new discoveries each year and contributing to the long-term monitoring needed to detect orbital decay in previously discovered planets. Detecting orbital decay requires measuring transit times with precision better than 1 minute and comparing observations separated by many years to detect shifts of tens of seconds accumulated over that baseline. The measurement challenge is substantial. Transits lasting a few hours must be timed to better than 1 part in 1,000, and systematic effects like star spots or stellar activity can create false signals that mimic orbital decay, if not carefully accounted for. The transit timing method compares observed transit times to predictions based on a constant orbital period, calculating when each transit should occur if the orbit was stable, and measuring the difference between predicted and observed times. A consistent pattern of early arrivals indicates that the orbital period is decreasing and the orbit is decaying. Only a handful of planets have confirmed orbital decay as of current observations. WASP-12b and Kepler 1658b being the most well-established cases, with a few others showing suggestive but not yet conclusive evidence. The small number of confirmed cases does not mean orbital decay is rare. Rather, it reflects the observational challenge of detecting the effect, which requires both a planet close enough to experience measurable decay and a long enough observational baseline to accumulate detectable shifts. Most hot Jupiters have not been observed long enough to detect orbital decay, even if it is occurring, and many are too distant or around too faint stars for the required precision to be achievable with current instruments. As time passes and observational baselines grow longer, more planets will show detectable orbital decay. Astronomers expect that within a decade or two, the number of confirmed cases will grow from a handful to dozens or more. Every planet discovered adds to the potential sample, and every year of additional observations extends the baseline, making previously undetectable decay measurable. The field is positioned to undergo significant growth as datasets mature and as new analysis techniques extract more information from existing observations. Revisiting old data with new methods has already proven valuable. The confirmation of Kepler 1658b's decay came partly from reanalyzing Kepler data with improved techniques. Radial velocity measurements complement transit observations by measuring the star's motion caused by the planet's gravity. The star and planet orbiting their common center of mass, causing the star to move in a small orbit that shifts its spectrum through Doppler effects. Measuring the radial velocity precisely over many years can detect changes in the planet's orbital period independently from transit timing, providing a second method to confirm orbital decay and to measure the star's tidal properties. The radial velocity method is challenging for distant faint stars, but works well for nearby bright stars, creating a complementary sample to transit surveys. Spectroscopic observations during transits can detect extended atmospheres and escaping material by measuring how the planet's atmosphere absorbs starlight at different wavelengths. The absorption creating deeper transits at certain wavelengths where atmospheric gases are opaque. Observing transits in ultraviolet light reveals hot gases and ionized metals in extended atmospheres, evidence for atmospheric escape and mass loss. These observations help identify which planets are losing their atmospheres rapidly and which might be at risk even if orbital decay has not yet been confirmed, extending the catalogue of potentially doomed worlds beyond just those with measured decay. The James Webb Space Telescope, launched in late 2021, brings unprecedented capabilities for studying exoplanet atmospheres through transit spectroscopy. Its infrared instruments able to detect molecules and measure atmospheric temperatures and compositions with far greater precision than previous instruments. JWST can observe hot Jupiter atmospheres in detail, detecting water vapor, carbon monoxide, methane, and other molecules, and measuring temperature profiles across the day and night sides. While JWST is not optimized for detecting orbital decay directly, its atmospheric observations can identify planets experiencing intense heating and atmospheric escape, helping prioritize which planets to monitor for possible decay. Future missions and facilities will improve our ability to detect and study doomed planets. Ground-based, extremely large telescopes, currently under construction, will enable precise radial velocity measurements and direct imaging of some hot Jupiters. While proposed space missions may include long-term monitoring programs specifically designed to detect orbital changes, the field is entering a phase where detecting orbital decay will transition from being a rare achievement to being a routine measurement for suitable planets, creating large statistical samples that will enable detailed studies of how tidal evolution works and how common planetary destruction is. The question of how many hot Jupiters are actually doomed remains open. Current estimates based on theoretical models and the few confirmed cases suggest perhaps 1 to 5% of hot Jupiters are close enough to experience destruction within a few million years, but the uncertainty is large. As more planets show confirmed decay, and as surveys become more complete, the statistics will improve, allowing astronomers to determine what fraction of hot Jupiters are doomed and what properties correlate with doom. Understanding the demographics of doomed planets will help refine migration theories and will reveal how common it is for migration to bring planets too close to their stars. The discovery of each new doomed planet provides an opportunity to study the destruction process at a different stage or in a different environment. Some planets might be caught early in their decay, with millions of years remaining. Others might be farther along with less time left. And the variety of examples will help astronomers understand the full sequence from stable hot Jupiter to decaying orbit to final destruction. No planet has yet been observed in the final rapid phase. Just before breakup, all current examples have millions of years remaining. But as the sample grows, it becomes more likely that a planet in the final stages will be found. The patient work of monitoring planets year after year, measuring transit times with precision, analyzing data for systematic effects, and comparing observations across long baselines represents the unglamorous but essential foundation of discovering doomed worlds. Telescopes point at the same stars night after night, recording the same transits repeatedly, building up the dataset needed to detect tiny changes in orbital periods. Astronomers carefully calibrate their instruments, account for stellar activity and instrumental effects, and test their methods with simulations to ensure the detected signals are real. The process takes time and dedication. The results often come in years or decades after observations begin. But the payoff is discovering planets in the process of destruction and measuring the physics of tidal evolution directly. Watching from Earth as telescopes monitor distant stars, you participate in a form of cosmic archaeology and prophecy combined. Observing the present state of systems, but using those observations to reconstruct their past migration histories and predict their future destruction. The light arriving from WASP-12b left that system over 1,000 years ago, carrying information about the planet's size, orbit, and atmospheric escape encoded in subtle variations in brightness and spectrum. Astronomers decode that information, extracting facts about temperature, composition, orbital period, and decay rate from the patterns of light, turning photons into knowledge about a doomed world. And this knowledge accumulates into understanding about how planetary systems live and die throughout the cosmos. You have journeyed from WASP-12b's distorted egg shape through other doomed worlds. From Kepler 1658b, orbiting its aging star, to ultra-short period planets racing around their suns. From the migration processes that brought these planets too close to the observations that revealed their fates. The story of doomed planets is ultimately a story about the dynamic nature of planetary systems and the variety of outcomes possible when planets form and evolve around stars. These worlds are not failures or mistakes. They are natural outcomes of physical processes playing out across billions of years. Matter organizing itself into planets and then reorganizing in response to gravity and tidal forces. Systems evolving from their initial conditions toward new states that sometimes include planetary destruction. Planetary doom, when it occurs, unfolds over timescales of millions of years, incomprehensibly long by human standards, yet brief on cosmic timescales, a blink in the life of a star or galaxy. WASP-12b has perhaps 3 million years remaining before its final disintegration. And during that time, the planet will continue orbiting as it has for billions of years, losing material slowly, spiraling inward gradually, existing as a world until the moment when tidal forces finally overcome its structure. For the planet, if planets could experience time, the remaining 3 million years might feel like an eternity, more than enough time for continents to form and erode on Earth, for species to evolve and go extinct, for human civilizations to rise and fall thousands of times over. Yet measured against the age of the universe, 13.8 billion years, or even against the age of the planet itself, likely several billion years, 3 million years is almost nothing. The processes destroying these planets are not malicious or tragic. They are simply physics, gravity and tidal forces operating according to mathematical laws that care nothing for preservation or destruction. Matter responding to forces in the ways it must. The star does not consume its planet with intent or awareness. The star simply exists and exerts gravitational force, and the planet responds by distorting and losing altitude and eventually disintegrating. No consciousness guides the process. No purpose drives it. Physics alone determines what happens. Equations of motion, unfolding as they must. The destruction is natural in the deepest sense, neither good nor bad, but simply the inevitable outcome when certain conditions are met. Understanding doomed planets helps astronomers understand the full life cycle of planetary systems, from formation in protoplanetary disks through billions of years of stable existence to eventual disruption through migration, tidal effects, or stellar evolution. Not all planets are doomed. Most planets in the galaxy probably enjoy stable orbits for billions of years until their host stars die. And even then, some planets may survive as orphans around white dwarfs or dispersed into interstellar space. The doomed planets represent a minority, special cases where the specific combination of migration history and tidal environment creates conditions for destruction. But this minority teaches us about processes that affect all planetary systems to some degree. Our own solar system appears stable. The planets have settled into orbits that should persist for billions more years, long enough for the sun to exhaust its core hydrogen and evolve off the main sequence. Earth orbits at 1 astronomical unit, far enough from the sun that tidal effects are negligible. And while the moon is slowly drifting away from Earth due to tidal forces, the effect is weak enough that the system remains essentially stable. Jupiter and Saturn are likewise stable at their current distances. tidal forces between them and the Sun being far too weak to cause significant orbital evolution on solar system timescales. The inner rocky planets, Mercury, Venus, Earth, and Mars, all orbit outside the zone where tidal destruction is possible. Their orbits secure for the foreseeable future. Yet even Earth has an expiration date written in the Sun's evolution, not from orbital decay, but from the Sun's eventual transformation into a red giant. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around an inert helium core, causing the outer layers to expand into a red giant, perhaps 100 times the current radius. This expansion will engulf Mercury and Venus with certainty, and possibly Earth as well, depending on details of how much mass the Sun loses during the expansion and how much Earth's orbit expands in response to that mass loss. Whether engulfed or merely scorched, Earth will be rendered uninhabitable long before the red giant phase through the Sun's gradual brightening. Increased solar luminosity, raising Earth's temperature and eventually boiling the oceans. Perhaps 1 billion years from now, the doomed planets remind us that nothing in the universe is truly permanent. Everything exists in a temporary state. Stars form and die, planets form and sometimes are destroyed. Galaxies merge and evolve, the cosmos continually changing over the vast expanses of time. This impermanence is not sad or troubling when viewed with cosmic perspective. It is simply the nature of a universe governed by physical law, where entropy increases and systems evolve and nothing remains unchanged. WASP-12b has existed for billions of years already, longer than complex life has existed on Earth, and its remaining few million years of existence far exceed the span of human civilization. The planet has had a long existence by any reasonable measure, and its eventual destruction is just another chapter in the ongoing story of matter organizing and reorganizing in response to fundamental forces. The scientific value of studying doomed planets extends beyond the intrinsic interest of watching worlds be destroyed. These planets provide unique laboratories for studying tidal physics, atmospheric escape, planetary interiors, and migration processes under extreme conditions. The measurements of orbital decay for WASP-12b and Kepler-1658b test theories of tidal dissipation in stars, helping astronomers understand how efficiently stars dissipate tidal energy, and how this efficiency varies with stellar mass, age, and structure. The atmospheric observations revealing mass loss and extended atmospheres inform models of atmospheric escape applicable to many exoplanets, not just doomed ones. The existence of doomed planets at all confirms that migration can bring planets too close and reveals what happens when it does. The future of doomed planet research is bright. The field is young and growing. New discoveries will add to the small current sample. Long-term monitoring will reveal decay in planets where it is currently too subtle to detect, and improving instruments will enable more precise measurements and more detailed atmospheric characterization. Within a decade or two, the number of confirmed doomed planets will likely grow from a handful to dozens, providing statistical samples large enough to determine how common the phenomenon is and what factors correlate most strongly with doom. Future observations might even catch a planet in the final stages of disruption, watching as it actively tears apart over decades or centuries. an incredibly rare opportunity to witness planetary death in real time. The doomed planets are a reminder that the universe is an active and dynamic place where dramatic events unfold constantly on timescales both long and short. From the 3 million year countdown to WASP-12b's destruction, to the rapid 11-hour orbit of K2137b racing around its star. These planets exist now, orbiting their stars, glowing in the darkness, losing atmosphere, spiraling inward, experiencing their final million years of existence. They are as real as Earth, as physical as the Moon, actual places where matter exists and physics operates, worlds we can observe and study and understand, even though we will never visit them, and they will be gone long before any signal we send could reach them. The sense of peaceful acceptance that comes from understanding these doomed worlds is part of the value of astronomy and science more broadly. Learning how the universe works and what happens within it provides perspective on our own existence and our own temporary presence in the cosmos. WASP-12b will be destroyed in 3 million years. The Sun will die in 5 billion years. The universe itself may eventually run down in a heat death trillions of years hence. And all of this is natural and expected, and not frightening when understood as the working out of physical law over vast time. We are part of this universe, made of matter that formed in stars, living on a planet that will someday be uninhabitable, observing other planets that are being destroyed, all of it connected through the same fundamental physics. The doomed planets continue their orbits tonight, as they have for billions of years, and will for millions more. WASP-12b glowing hot and egg-shaped in its close embrace with its star. Kepler 1658b racing around its subgiant host, ultra-short period planets completing their rapid circuits, all of them existing in the present moment while carrying within their physics the certainty of eventual destruction. The universe is filled with such worlds, planets in various stages of doom, some just beginning their decay, others far along, some perhaps experiencing their final days right now as we observe. The cosmic process of planetary destruction ongoing throughout the galaxy. These planets join the even larger population of stable worlds that will survive for billions of years. The full diversity of planetary fates, represented among the trillions of planets orbiting stars throughout the cosmos. Contemplating doomed worlds brings a quiet sense of wonder mixed with the peaceful recognition of impermanence. Everything that exists will eventually change or end, yet existence continues. New stars form to replace those that die. New planets form around those stars, the cycle continuing indefinitely into the future. WASP-12b will be destroyed, its atoms merging into its star, participating in fusion reactions, some becoming helium and energy, others remaining as carbon or oxygen or iron mixed into the star's outer layers. Eventually, the star will die as well, billions of years hence, shedding its outer layers and leaving behind a white dwarf that will cool for trillions of years. The atoms that were once part of WASP-12b will spread into space as part of the planetary nebula, perhaps someday becoming part of new stars or planets forming from the enriched gas. Nothing is truly lost, just transformed. The journey through doomed worlds ends here with acceptance and understanding, rather than fear or sadness. These planets show us one possible fate among many in the diverse outcomes of planetary system evolution. They exist now. They have existed for billions of years. They will exist for millions more. And then they will transform into something else. The universe continues its patient unfolding, stars and planets forming and dying according to physical law. And we are fortunate to live in a time when we can observe and understand these processes. WASP-12b glows in space, 1,400 light-years away, the light from its hot atmosphere traveling toward us, carrying information about a doomed world that will continue orbiting its star long after every human civilization has ended. The planet's fate, independent of any observer, physics operating whether anyone watches or not. Rest now in the knowledge of doomed worlds, planets stretched into eggs and slowly consumed by their stars, the quiet understanding that everything exists temporarily, and that this impermanence is natural and expected and part of the beauty of a universe governed by comprehensible physical law. Sleep well under a sky where planets orbit, some forever safe, some doomed to eventual destruction. All of them part of the ongoing cosmic story of matter and energy organizing and reorganizing across the vastness of space and time. The doomed planets continue their patient spirals inward, existing in their final million years, and the universe remains beautiful and understandable, and filled with wonders both permanent and temporary. And that is enough.